What if everything you thought you knew about reality was only a fraction of the story? Picture a universe where time doesn't just move forward but can loop back on itself, where your own consciousness might be actively shaping the world around you, and where space itself is threaded with dimensions beyond our perception. These aren't just ideas from science fiction, they're real, groundbreaking concepts that physicists, philosophers, and cosmologists are exploring right now. Concepts that shake the very foundations of how we understand existence. Today, we're setting off on a journey through 30 of the most astonishing, mind-expanding ideas in modern science, theories, and discoveries that reshape our understanding of space, time, reality, and consciousness itself. We'll venture into the strange, counterintuitive world of quantum mechanics, where particles communicate instantaneously across vast distances and where reality remains uncertain until it's observed. We'll dive into cosmic mysteries like dark matter and dark energy, invisible forces that make up most of the universe yet remain almost entirely hidden from our view. And we'll question the nature of our own minds, exploring theories that suggest consciousness might not just be a product of the brain, but a fundamental part of the cosmos. This isn't just a list of facts, it's an invitation to rethink what's possible. Each one of these ideas opens a door to a new way of seeing the world, challenging assumptions we often take for granted. By the end of this journey, you may find yourself looking at the night sky, the passage of time, or even your own thoughts in a completely new light. So settle in, open your mind, and get ready to explore the edges of human understanding where mystery and wonder await at every turn. Now, let's start with one of the most baffling and well-established phenomena in all of physics, quantum entanglement. It's a concept so strange that it seems to rip up the very rulebook of how we think the universe operates. Imagine you have a pair of particles, let's say 2 electrons, that are born together or interact in a specific way. They become intimately linked, their fates intertwined. Now, send one of these particles on a journey to the farthest star in a distant galaxy, while its partner remains here on Earth. According to the rules of quantum mechanics, if you then measure a property of the local particle, say, its spin, you will instantly know the corresponding property of its partner, no matter how many light years away it is. It's as if an invisible thread connects them, allowing information to be shared faster than the speed of light. This idea was so unsettling to the scientific establishment, particularly to Albert Einstein, that he famously derided it as spooky action at a distance. For Einstein, this instantaneous connection violated the fundamental principle of locality, the idea that objects are only influenced by their immediate surroundings and that no information can travel faster than light, the universe's ultimate speed limit. He, along with colleagues Boris Podolsky and Nathan Rosen, proposed this as a paradox in 1935, arguing that it revealed quantum mechanics must be an incomplete theory. They believed there must be some hidden variables, underlying properties we hadn't yet discovered, that predetermined the states of the particles and eliminated the need for any spooky long-distance communication. But here's where the story gets even more fascinating. For decades, this was largely a philosophical debate. Then, in the 1960s, a physicist named John Stuart Bell devised a way to test it. Bell's theorem provided a mathematical framework for an experiment that could determine who was right: Einstein, with his hidden variables and local reality, or the quantum pioneers like Niels Bohr, who embraced the weird, interconnected nature of the subatomic world. The crux of Bell's test was to measure entangled particles in many different directions. If hidden variables existed, the results would fall within a certain statistical range. If quantum mechanics was correct and the particles were truly spookily connected, the results would violate that range. When technology finally caught up in the 1970s and 80s, experiments by teams led by scientists like Elaine Aspect began to be conducted. The results were clear and revolutionary. Bell's inequality was violated. The particles were correlated in ways that no local hidden variable theory could ever explain. The universe had chosen the spooky option. These findings have been confirmed again and again with ever-increasing precision, effectively proving that entanglement is a real, fundamental feature of our reality. This isn't just a theoretical curiosity. It's a bedrock principle that has given birth to entire new fields of technology, like quantum computing and quantum cryptography. In quantum encryption, for instance, any attempt to eavesdrop on a message sent using entangled particles would immediately disrupt their delicate connection, alerting the users to the presence of a spy. It's a technology that leverages the weirdness of the quantum world to create potentially unbreakable codes. So what does this mean for our understanding of the cosmos? Quantum entanglement suggests that at the most fundamental level, the universe may not be composed of separate, independent things. Instead, it points toward a deeply interconnected whole, a cosmic fabric where the idea of true separation might be nothing more than an illusion. It challenges our most basic intuitions about space, distance, and individuality, hinting that we are all part of a vast, intricate, and non-local web of existence. But if entanglement suggests a universe more deeply connected than we ever imagined, the next concept takes that idea and explodes it out to a literally infinite scale. What if every possible outcome of every possible event isn't just a potential but an actuality, playing out in a reality of its own? This is the staggering proposition of the multiverse theory. Forget a single universe. Picture instead a vast, perhaps infinite, cosmic tapestry where every version of reality you can conceive, and countless more beyond human imagination, are all real and happening right now. In one universe, you might be reading this script. In another, you're an astronaut on a mission to Europa. And in another, the very laws of physics are so different that matter as we know it never even formed. The scientific underpinnings for this mind-bending idea don't come from a single source but emerge from several different branches of physics, each pointing toward a plurality of worlds. One of the most prominent versions is the many-worlds interpretation of quantum mechanics, proposed by a brilliant and somewhat rebellious young physicist named Hugh Everett in 1957. Everett was deeply unsatisfied with the prevailing Copenhagen interpretation, which said that a quantum particle exists in a blurry superposition of states until the moment it is observed, forcing it to choose a single reality. To Everett, this introduction of an observer to collapse the wave function seemed arbitrary and unscientific. Why should consciousness have a special role? His radical solution was elegant and, in a way, simpler. The wave function never collapses. Instead, at the moment of a quantum event like measuring the spin of an electron, the universe itself splits. One branch continues where the electron is spinning clockwise. An entirely new, equally real branch is created where it is spinning counterclockwise. The observer, too, splits, each one experiencing a different, definite outcome. Apply this to every quantum event happening everywhere, all the time, and you get an exponentially exploding tree of reality, with every possible history and future unfolding simultaneously. This isn't just confined to the quantum realm. Consider the famous thought experiment of Schrödinger's cat. In the classic version, the poor cat in the box is suspended in a state of being both alive and dead until someone looks inside. But in the many worlds view, there is no suspension. there are two real, separate universes from the moment the radioactive atom might or might not decay. In one universe, a scientist opens the box to find a living cat and feels relief. In the other branch, a different version of that same scientist opens the box to find a dead cat and feels grief. Both experiences are equally real. This interpretation completely removes the mystery of the wave-function collapse but replaces it with the breathtaking, and to some, unsettling, idea that we are constantly branching into countless copies of ourselves, each unaware of the others. Beyond the quantum world, cosmology offers another pathway to the multiverse through the theory of cosmic inflation. This is the idea that in the first tiny fraction of a second after the Big Bang, the fabric of space-time underwent a period of exponential, faster-than-light expansion. Leading physicists like Andre Linde suggest that this inflation might not be a one-time event but an eternal process. In this eternal inflation, the overall multiverse is like a vast, bubbling cauldron of space-time. Regions of this inflating field can randomly stop inflating and pinch off to form their own separate bubble universes. Our entire cosmos, with its hundreds of billions of galaxies, might just be one bubble in a frothy sea of infinity. And crucially, each of these bubble universes could have randomly landed on a different set of physical constants and laws. In some, the force of gravity might be too strong for atoms to hold together. In others, the nuclear forces might be too weak to form stars. We find ourselves in a universe with just the right rules to allow for stars, planets, and life, not because of luck, but because in an infinite multiverse, every possible combination must exist somewhere. This is known as the Anthropic principle. We can only observe a universe compatible with our existence. The implications of this are enough to make your head spin. It redefines concepts of fate and identity on a cosmic scale. Every choice you've ever made, from what you had for breakfast to your career path, was made differently in another branch of the multiverse. There's a version of you who took that other job, who said yes instead of no, who never even met their partner. This doesn't necessarily diminish our choices. In a way, it makes every possibility valid and real. It also poses profound questions about free will. If every decision branch is taken, is it truly a choice, or are we just passengers riding one path on an infinite tree? Furthermore, the multiverse theory, while solving some puzzles like the fine-tuning of our universe, has its critics. Some argue it is not falsifiable. If we can never contact or detect these other universes, does it even qualify as science? Others find the idea of infinite copies to be philosophically untenable. Yet, it remains one of the most compelling and debated frontiers in theoretical physics, a testament to our relentless drive to understand the true nature of the reality we call home. But if the multiverse suggests a reality of infinite possibilities, the simulation hypothesis asks an even more direct and unsettling question: what if none of it is real? This idea pushes past the boundaries of physics and into the realms of philosophy and futurism, proposing that our entire universe, with all its richness and complexity, might be nothing more than an elaborate digital construct. Think of the most immersive video game or virtual reality experience you've ever had, and then imagine that level of realism advanced by thousands or even millions of years. Now consider that we might be the characters inside such a simulation, completely unaware that our world is rendered in code rather than atoms. The modern argument for this hypothesis was laid out most famously by the philosopher Nick Bostrom of Oxford University in 2003. He didn't claim we are definitely in a simulation, but rather presented a compelling logical trilemma. He argued that at least one of three propositions must be true. First, that almost all civilizations at our level of technological development go extinct before they achieve the capability to create realistic simulations. Second, that even if they achieve that capability, they almost certainly choose not to run such simulations, perhaps for ethical reasons. Or third, we are almost certainly living in a computer simulation right now. The reasoning is statistical. If a civilization survives and progresses to a post-human stage, it could potentially harness the energy of entire stars to power unimaginably powerful computers. With that kind of processing power, it could run vast numbers of highly detailed simulations of its own ancestors or other conscious beings. The number of simulated minds in such a scenario would quickly dwarf the number of original biological minds. Therefore, if you believe that the first two options are unlikely, that civilizations will survive and that they will choose to run simulations, then the odds are overwhelming that you are one of the simulated minds, not one of the original biological ones. This isn't just a thought experiment confined to academic papers. The concept has been embraced and popularized by prominent figures in the tech world, most notably Elon Musk, who has stated that the odds we are in base reality are 1 in billions. His reasoning echoes Bostrom's statistical argument. Given the rapid pace of our own technological advancement in graphics and virtual reality, it seems plausible that a sufficiently advanced civilization could create a simulation indistinguishable from reality. If that's possible, then it is statistically likely that we are already inside one. But this leads to some profound and deeply puzzling questions. The first is the technological feasibility itself. Could a consciousness with its rich inner life of sensations, emotions, and thoughts truly be simulated? This gets to the heart of the philosophy of mind. If consciousness is simply the product of information processing, a view known as functionalism, then yes, given enough computing power, you could replicate the functions of a human brain and create a simulated being that is just as conscious as you or I. This is a central assumption of the hypothesis, but if consciousness is something more, something intrinsic and non-computable, then the whole premise begins to fray. Beyond the technological hurdle, the simulation hypothesis forces a radical re-evaluation of the nature of reality. If our universe is a simulation, then the fundamental building blocks of existence are not quarks or strings, but bits of information. The laws of physics are not discovered truths about the universe. They are the underlying rules of the simulation's programming. Glitches in this program might explain seemingly paranormal events or even quantum weirdness. Perhaps the uncertainty principle is simply the program conserving processing power by not rendering definite states until they are observed. This idea, sometimes called quantum vagueness, suggests that the simulation only fills in the details when someone is looking, much like a video game only renders the part of the world the player can see. This concept also spirals into infinite regress. If we are in a simulation, who is to say that the civilization that created us isn't itself inside a simulation, created by an even higher civilization? We could be in a nested series of simulations like a cosmic set of Russian dolls with no way of knowing what, if anything, lies at the very top, the true base reality. And this opens up a Pandora's box of ethical questions. If we are simulations, do our lives have intrinsic meaning, or are we merely entertainment or experimental subjects for our creators? What responsibilities do those creators have toward us? If they were to shut down the simulation, would it be an act of mass murder? Conversely, if we one day develop the capability to create such simulations ourselves, would creating conscious beings for our own purposes, even in a digital world, be a form of slavery? The simulation hypothesis ultimately does more than just question the substance of our reality. It challenges us to define what real even means. If a simulated mind believes it is real, feels pain and joy, and forms relationships, is its experience any less valid than our own? This idea blurs the line between reality and illusion in a way that is both terrifying and liberating, suggesting that the search for meaning might not be about discovering an external truth, but about understanding the nature of the experience itself, regardless of its source. Now, let's shift our focus from the nature of reality itself to the very fabric of our experience within it, time. We all live by the steady, reassuring tick of the clock, a universal rhythm that seems to govern everything from our daily schedules to the aging of the stars. But what if that rhythm isn't universal at all? What if time itself is flexible, stretching and compressing based on how fast you're moving or how deep you are in a gravitational field? This isn't science fiction. It's a proven, measurable phenomenon known as time dilation, a cornerstone of Einstein's theory of relativity that completely shatters our everyday intuition. The story begins with a thought experiment that revolutionized physics. Imagine you're standing on a platform watching a train car speed by. Inside that car, a passenger turns on a flashlight, pointing it directly at a mirror on the opposite wall. From your perspective on the platform, the light doesn't just go straight up and down. Because the train is moving, the path of the light beam appears to you as a diagonal. It goes up and forward as the train moves, hits the mirror, and then comes back down and backward along another diagonal. This path is longer than the simple up and down path the passenger inside the train observes. Since the speed of light is an absolute constant in the universe, a law that never changes, the only variable left to account for this difference is time itself. For the light to cover that longer, diagonal path from your perspective, more time must have passed for you on the platform than for the person on the train. Time for the moving passenger has literally slowed down. This is the essence of time dilation due to relative motion, a concept that feels alien because at our slow, everyday speeds, this effect is immeasurably tiny. But as you approach the cosmic speed limit, the speed of light, this effect becomes dramatic. This leads us to the famous twin paradox. Picture two identical twins. One remains here on Earth, living a normal life. The other embarks on a journey into deep space aboard a rocket capable of traveling at 90% the speed of light. After exploring a distant star system for a while, the astronaut twin turns around and comes back home. For the traveling twin, perhaps only 10 years have passed. But due to the effects of time dilation, when they land back on Earth, they might find that their stay-at-home sibling has aged 30 years. The astronaut is now 20 years younger than their own twin. This isn't a trick of biology or perception. It's a fundamental property of space-time. The clocks on the spaceship literally ticked more slowly relative to the clocks on Earth. We even see a miniature version of this happening right above our heads. Astronauts on the International Space Station, orbiting the Earth at about 17,000 miles per hour, experience time very slightly slower than we do on the surface. The difference is minuscule. They gain about 0.001 seconds every 3 months, but it is measurable with incredibly precise atomic clocks, providing daily confirmation of Einstein's brilliant insight. But motion is only half the story. The other powerful force that warps time is gravity. Einstein's general theory of relativity tells us that gravity isn't just a force pulling on objects. It is a curvature of space-time itself caused by mass and energy. Think of the universe as a giant, stretched rubber sheet. A massive object like a star or a planet creates a deep dip in that sheet. Just as a marble would roll toward a bowling ball sitting in that dip, objects are drawn toward masses by the curvature of space. And this curvature affects time as well. The closer you are to a massive object, the stronger the gravitational field, and the more time slows down. Your head, being slightly farther from Earth's center of gravity than your feet, actually ages faster than your feet by a tiny fraction of a nanosecond over a lifetime. This effect, called gravitational time dilation, is crucial for the technology we use every day. The Global Positioning System, or GPS, is a network of satellites that must provide incredibly precise location data. These satellites are orbiting in a weaker gravitational field than receivers on the ground, so their onboard atomic clocks run faster by about 45 millionths of a second per day. If the engineers didn't constantly correct for both this gravitational effect and the time dilation from the satellite's orbital speed, the entire system would become useless, accumulating errors of several miles within just a few hours. Our navigation apps work because we have to account for the fact that time itself runs at different rates in different places. The most extreme example of this gravitational time warp is found at the edge of a black hole. Here, gravity is so intense that the fabric of space-time is curved into a bottomless pit. From the perspective of a distant observer watching an object fall toward a black hole, time for that object would appear to slow down more and more, grinding to an infinite halt at the event horizon. The object would seem to freeze, fading to red and then disappearing from view, never quite crossing that final threshold from our point of view. For the object itself, of course, time would proceed normally, and it would cross the event horizon and meet its fate. This stark difference in the experience of time highlights the profound truth that there is no single, universal now. The flow of time is a local experience dependent entirely on your state of motion and your position within a gravitational field. This radical idea leads to a breathtaking view of the universe known as the block universe theory. If time can stretch and compress, then the distinction between past, present, and future might be nothing more than a persistent illusion of human consciousness. In this four-dimensional picture, space-time is a static, unchanging block. Every event that has ever happened or ever will happen, the birth of the universe, the fall of the Roman Empire, your first day of school, the death of the sun, all exist simultaneously within this block. We, as conscious beings, simply experience this reality one slice at a time, like a needle reading the grooves on a vinyl record, creating the subjective feeling of a flowing present. This challenges our deepest notions of free will and destiny. If the future is already out there, just as fixed and real as the past, what does that say about our choices? It forces us to confront the possibility that the passage of time is not a fundamental feature of the universe, but rather a feature of our own minds as we navigate an eternal, frozen landscape of events. But if time itself is a flexible and relative construct, what then is the role of the conscious observer in shaping the very reality it perceives? This brings us to one of the most profound and debated ideas at the frontier of science and philosophy, the notion that consciousness itself might be the fundamental force that collapses quantum possibilities into the solid, definite world we experience. This concept, most famously associated with the Copenhagen interpretation of quantum mechanics, suggests that the act of observation is not a passive recording of events but an active participant in the creation of reality. To understand this, we must revisit one of the most iconic experiments in all of physics, the double-slit experiment. The setup is deceptively simple. A barrier with two thin, parallel slits is placed in front of a detector screen. Then you fire a beam of particles, say electrons or photons, at the barrier. If these particles were tiny bullets, as classical physics would predict, you would expect to see two distinct bands of hits on the screen behind the two slits. But that's not what happens. Instead, what appears is a stunning interference pattern of alternating light and dark bands. This is a pattern characteristic of waves, not particles. It's as if each individual particle is passing through both slits at the same time, like a wave, and interfering with itself on the other side. This bizarre behavior demonstrates the core quantum principle of superposition, that a particle exists in a blur of all possible states and locations until the moment it is forced to choose one. Now, here is where the experiment takes a truly mind-bending turn. Scientists decided to place a measuring device by the slits to determine which specific slit each particle actually goes through. The moment they do this, the beautiful interference pattern vanishes. In its place, the screen shows only two distinct bands, just as if the particles were little bullets. The mere act of observing, of gathering information about the particle's path, seems to force it to abandon its wave-like behavior and act like a single, definite particle. It's as if the particle knows it is being watched and changes its behavior accordingly. This is the infamous quantum measurement problem. What exactly constitutes a measurement? Is it the physical interaction with the detector, or is it the conscious awareness of that information by an observer? This is where the Copenhagen interpretation, formulated by pioneers like Niels Bohr and Werner Heisenberg, places consciousness at the center of the stage. They propose that the wave function, the mathematical description of a particle's quantum state, doesn't describe a physical reality, but rather a set of probabilities. It only collapses into a single, definite reality upon observation. In this view, there is no concrete world out there independent of our looking at it. The moon is not there when nobody is looking. Reality remains in a suspended state of potentiality until a conscious mind interacts with it, effectively bringing it into existence. The physicist John Wheeler took this idea even further with his delayed choice thought experiment. Imagine a version of the double-slit where we wait to decide whether to measure the particle's path until after it has already passed through the slits but before it hits the screen. Astonishingly, the results show that our choice in the present seems to retroactively determine how the particle behaved in the past. The decision to observe or not to observe changes history, suggesting that no quantum phenomenon is truly a phenomenon until it is an observed phenomenon. This radical proposition that mind and matter are inextricably intertwined naturally spills over from the lab into broader philosophical and even spiritual realms. For centuries, various Eastern philosophies and mystical traditions have posited that consciousness is the primary substance of the universe. The ancient Hindu concept of Maya, for instance, suggests the physical world is an illusion, a grand play of consciousness. The idea that focused intention can influence physical reality is a cornerstone of many meditative and manifestative practices. While these claims remain highly controversial and largely unproven by rigorous scientific standards, they resonate with the quantum enigma. If a single observer can collapse a particle's wave function, could the collective intention of many minds influence larger, more complex systems? Some interpretations of the placebo effect, where belief alone triggers real physiological healing, could be seen as a macroscopic echo of this quantum principle, where mind directly influences matter. However, it is crucial to distinguish the scientific debate from more speculative leaps. Most modern physicists are deeply uncomfortable with giving consciousness such a primary role, often called the consciousness causes collapse interpretation. They point out that there is no known mechanism for how a non-physical mind could influence a physical system. The more mainstream, albeit still strange, explanation is decoherence. This theory suggests that the collapse isn't caused by consciousness, but by inevitable interactions with the environment. The moment a quantum system bumps into even a single other particle, its delicate superposition is destroyed and it behaves classically. In the double-slit experiment, it is the interaction with the measuring device that causes decoherence, not the human mind becoming aware of the result. The observer is just reading the result of a physical process that has already happened. Yet, this doesn't entirely solve the puzzle, it just pushes it back a step. We are still left with the question of what reality is like in the absence of any interaction at all. The debate forces us to confront the deepest questions about the nature of existence. Is the universe a cold, objective mechanism that operates regardless of us? Or is it a participatory universe, as John Wheeler called it, where we are all necessary collaborators in the ongoing creation of everything we see and know? This concept doesn't just warp our understanding of space and time. It places us, the observers, right at the heart of the cosmic mystery, suggesting that the line between the inner world of the mind and the outer world of the cosmos might be the most profound illusion of all. Yet this bizarre connection and the strange role of the observer are built upon a foundation of rules that we believe are unbreakable, laws that govern the very consistency of the universe itself. One of the most sacred principles in all of physics is the conservation of information. In the quantum world, information isn't just data. It's the complete set of properties that define every single particle, its mass, its spin, its energy, its identity. The fundamental law states that information can never be truly created or destroyed. It can be transformed, scrambled, or spread out, but it must always, in principle, be recoverable. If you could somehow reverse all the motions and interactions in a system, you could always trace everything back to its original state. It's the ultimate cosmic receipt, ensuring that the universe's books are always balanced. This principle is so bedrock that the entire framework of quantum mechanics depends on it. Now, imagine throwing a book into a fire. The pages burn, the ink turns to smoke and ash. It seems like the information is gone, but a supreme physicist with perfect knowledge could, in theory, collect every single particle of smoke, measure the exact heat radiation, and trace the entire process backward to reconstruct every word on every page. The information was never destroyed, it was just chaotically rearranged. This is the unwavering rule that quantum mechanics demands. But for decades, physicists believed they had found the one object in the universe that could break this rule, a black hole. According to Einstein's general theory of relativity, a black hole is the ultimate endpoint of gravitational collapse. Its core is a singularity, a point of infinite density where the known laws of physics simply cease to exist. Surrounding it is the event horizon, a point of no return. Once anything, a spaceship, a planet, or just a single photon of light crosses that boundary, it is lost forever to our universe. It is irretrievably pulled into the singularity and seemingly erased from existence. This created a terrifying prospect. Throw that book into a black hole, and the information it contains would be truly and permanently destroyed, violating a cornerstone of quantum theory. For a long time, physicists uncomfortably accepted this, assuming the immense gravity of the black hole created a special exception to the rules. But then, Stephen Hawking stepped in and made the problem infinitely worse. In 1974, Hawking applied quantum theory to the edge of a black hole and made a shocking discovery. He realized that due to quantum fluctuations, black holes aren't completely black. Pairs of virtual particles constantly flicker in and out of existence everywhere in space, even in a perfect vacuum. Normally, they annihilate each other almost instantly. But at the very edge of the event horizon, something strange can happen. One particle of the pair might fall into the black hole while the other escapes into space. The particle that escapes carries away energy, and to conserve energy, the black hole itself must lose a corresponding amount of mass. This stream of escaping particles is what we call Hawking radiation. This was a monumental finding. Black holes slowly evaporate over astronomical timescales. A stellar mass black hole would take longer than the current age of the universe to evaporate, but eventually it would vanish completely in a final faint puff of radiation. And this is where the real paradox ignites. Hawking radiation is thermal. It's random and featureless, like the heat from a stove. It contains no information whatsoever about what fell into the black hole. Whether you threw in a library of encyclopedias or a heap of garbage, the Hawking radiation coming out would look exactly the same. So, when the black hole finally evaporates to nothing, what happened to all the information that ever fell in? According to Hawking's calculation, it is irrevocably lost. This became known as the black hole information paradox, and it set up a direct conflict between the two pillars of modern physics: Einstein's general relativity, which allows for information loss inside a black hole, and quantum mechanics, which forbids it with absolute certainty. Hawking himself famously bet against information conservation, convinced his math was correct. This launched a war of ideas that has raged for decades, a battle to save the soul of physics. If information can be lost, then the universe is fundamentally unpredictable and history cannot be retraced. The very foundation of reality would be built on sand. To resolve this, physicists had to propose even more mind-bending ideas. One of the most prominent solutions comes from the work of Leonard Susskind and others, and it's called the holographic principle. This theory suggests that when something falls into a black hole, its information isn't actually lost inside. Instead, it is somehow encoded and preserved in a scrambled, two-dimensional form on the surface of the event horizon, like a cosmic fingerprint. The three-dimensional information of the objects that fell in is projected onto the two-dimensional boundary of the black hole, much like a hologram where a 3D image is stored on a flat 2D surface. Then, as the black hole emits Hawking radiation, this radiation isn't random after all. It somehow carries away that encoded information, slowly and meticulously unpacking it back into the universe as the black hole evaporates. The information was never truly lost. It was just translated into an incredibly complex code that is finally redeemed. This idea is so powerful that it has been extended to the entire universe, suggesting that all the information within our three-dimensional cosmic volume might be encoded on its two-dimensional boundary at infinity. The holographic principle offers a breathtakingly elegant solution, but it forces us to accept that our perception of a three-dimensional reality might be a magnificent illusion, a projection from a deeper, lower-dimensional reality that we have yet to fully understand. The black hole information paradox, born from a conflict between our greatest theories, may ultimately be the key that unlocks a far deeper truth about the nature of reality, space, and information itself, pointing the way toward the long-sought theory of quantum gravity. Yet, even as we grapple with the idea that our entire universe might be a projection on a cosmic boundary, another theory emerges that questions not just the substance of reality, but the very nature of our own existence within it. This idea is perhaps one of the most unsettling thought experiments ever conceived, a hypothesis so strange that it seems to pull the rug out from under everything we think we know. It's called the Boltzmann brain, and it forces us to ask a terrifying question. Could you, the person having this very thought right now, be nothing more than a momentary, accidental flicker of consciousness in an otherwise empty and eternal void? The concept is named after the brilliant and troubled 19th-century physicist Ludwig Boltzmann, who made foundational contributions to the field of statistical mechanics. Boltzmann was wrestling with a deep puzzle about our universe, the arrow of time. We experience time as moving inexorably forward, from a state of order to a state of disorder. Milk mixes into coffee but never unmixes. Eggs scramble but never unscramble. This increase in disorder is known as entropy, and the universe as a whole is thought to be steadily evolving from a low entropy, highly ordered past toward a high entropy, chaotic future. But why was the past so ordered to begin with? Why did the universe start in such an incredibly unlikely, low entropy state? This is known as the past hypothesis problem. Boltzmann proposed a radical and, for its time, shocking solution. He suggested that our entire observable universe, with all its galaxies, stars, and planets, might itself be a rare but inevitable statistical fluctuation within a much larger and older cosmos that is, on average, in a state of maximum entropy and chaos, a featureless, lifeless soup of particles in perfect thermal equilibrium. In this eternal and static heat-death, random quantum fluctuations will occasionally cause particles to arrange themselves into orderly configurations. Most of these fluctuations are tiny and insignificant, but given enough time, an infinite amount of time, even the most wildly improbable events must occur. A collection of particles could randomly assemble into a fully formed, working refrigerator, or a diamond the size of a planet, or, and this is the crucial part, a fully functioning human brain, complete with all the neural pathways and electrical impulses that would give rise to a conscious experience, complete with a set of entirely fabricated memories of a life that never actually happened. This is the Boltzmann brain, a self-aware entity that pops into existence from the random jostling of particles, believes itself to be a person with a past and a future, exists just long enough to have a single coherent thought, perhaps the thought, "Why am I here?" and then almost instantly dissolves back into the featureless chaos from which it came. Its entire reality is an illusion, a cosmic accident. And here is the truly mind-warping part. In an infinite and eternal universe, these isolated, conscious fluctuations are statistically far more likely to occur than the spontaneous formation of an entire, ordered, 14-billion-year-old universe like our own. It is infinitely easier for random chance to assemble one working brain for a split second than it is to assemble trillions of galaxies, 100 billion stars, and a planet with a continuous history supporting life. Therefore, if the universe is eternal and static, the number of Boltzmann brains should vastly, overwhelmingly outnumber the number of real, biologically evolved brains embedded in a real cosmic history. So, if you're reasoning statistically, the odds are overwhelmingly against you being a real person in a real universe. You are far more likely to be a transient Boltzmann brain, hallucinating a world that doesn't exist. This is not just a philosophical curiosity. Modern cosmologists use it as a powerful tool to test our theories about the origin and ultimate fate of the cosmos. The current leading theory for the beginning of our universe is cosmic inflation, a period of rapid, exponential expansion that set up the low entropy initial conditions. The Boltzmann brain paradox is a serious challenge to this model. If our theory of the universe's evolution predicts that it will eventually reach a state of maximum entropy and exist in that state for an effectively infinite time, then that theory also predicts that Boltzmann brains will eventually become the dominant form of consciousness. Since we clearly do not observe ourselves to be such fleeting illusions, we see a coherent, structured universe with a consistent history. This suggests that our theory of an eternal future heat-death must be flawed. In other words, the fact that we exist as coherent observers in a stable universe is evidence that the universe must not be eternal and static. It might have a true beginning, or it might eventually cycle or reset in some way that prevents an eternal equilibrium. thereby saving us from the statistical nightmare of being mere illusions. The Boltzmann brain thought experiment is a profound and deeply humbling exercise. It forces us to confront the reliability of our most basic tools for understanding the world, our memories and our perceptions. How can you truly know that your past is real? How can you be certain that the world didn't just pop into existence 5 minutes ago, complete with all your memories and history books intact? This idea, known as the 5-minute hypothesis, is a less technical cousin of the Boltzmann brain. Both challenge the very foundations of empirical knowledge. We trust that our senses and memories provide a roughly accurate account of a real external world, but this thought experiment shows that this trust is ultimately a matter of faith. There is no logical way to prove you are not a Boltzmann brain. Ultimately, most scientists and philosophers reject the idea that we are actually such fleeting illusions, not because it can be disproven, but because it leads to a kind of intellectual paralysis. If we cannot trust any of our observations, then the entire project of science and reason collapses. The fact that our observations are coherent, consistent, and lead to successful predictions about the future is the best evidence we have that our reality is, in fact, real. The Boltzmann brain, therefore, stands less as a likely reality and more as a stark reminder of the incredible fine-tuning and unlikely nature of our ordered cosmos. It highlights the profound mystery of why there is a universe with a history at all, and why we are here to witness it rather than lost in an eternal, chaotic silence. It is a paradox that pushes our theories to their breaking point, demanding a more complete picture of cosmic reality, one where conscious observers are not just accidental glitches, but fundamental features of the story. But if the bizarre implications of the Boltzmann brain leave us questioning the very nature of our existence, string theory offers a radically different vision, one that seeks to unify all of reality under a single, elegant mathematical framework. This ambitious theory proposes a truly fundamental shift in our understanding of the universe's building blocks. For centuries, we've believed that the deepest level of reality is made of point-like particles, electrons, quarks, and photons, infinitesimal dots with no internal structure. String theory challenges this notion at its core. It suggests that if we could peer down to the tiniest possible scale, a scale trillions of times smaller than an atom, we would not find a dot. Instead, we would find a tiny, vibrating, one-dimensional loop of energy, a string. What makes this idea so powerful is that these strings aren't all identical. Just as a single violin string can vibrate at different frequencies to produce all the distinct notes of a musical scale, these fundamental cosmic strings can vibrate in an infinite number of different ways. And each distinct vibration pattern, each unique resonant frequency, manifests as a different kind of particle. One specific vibration gives rise to an electron. A slightly different vibration produces a quark. Another pattern creates a photon, the particle of light. In this breathtakingly simple and elegant picture, every single particle in the universe, every building block of every atom in every star and planet and person, is just a different note on the same tiny, vibrating string. The universe is not a collection of separate particles, it is a cosmic symphony. This beautiful idea holds the potential to solve the single greatest problem in modern physics: the unification of general relativity, which governs the immense scale of planets and galaxies, with quantum mechanics, which governs the bizarre world of the very small. These two pillars of 20th century physics are mathematically incompatible, leading to nonsensical infinities whenever they are forced to meet, such as at the center of a black hole. String theory naturally smooths out these infinities because its fundamental objects are not zero-dimensional points but one-dimensional strings, which interact in a much softer, more finite way. It doesn't just aim to describe some forces, it aspires to be a theory of everything, a single set of equations that describes all forces and all matter. However, this incredible promise comes with a truly mind-bending cost. The mathematics of string theory only works if the universe has more than the three spatial dimensions of length, width, and height that we experience every day. In fact, for the equations to be consistent and avoid absurdities, the theory requires a total of 10 or even 11 dimensions. This immediately raises an obvious and critical question. If there are all these extra dimensions, where are they? Why don't we see them? The most widely accepted answer is a concept known as compactification. The idea is that these extra dimensions are not vast and expansive like the three we know. Instead, they are curled up or compactified into an unimaginably tiny, complex shape at every single point in space. To understand this, think of a common everyday object, a garden hose. From a great distance, the hose looks like a simple one-dimensional line, but as you get closer, you realize it has a second dimension, its circumference curled up into a tiny circle at every point along its length. In the same way, at every point in our familiar three-dimensional space, there could be 6 or 7 additional spatial dimensions, curled up into a fantastically complex, tiny shape called a Calabi-Yau manifold. These dimensions are so small on the scale of the so-called Planck length that they are completely hidden from our view and our experiments, just as you can't see the circular dimension of a hose from a mile away. This framework also provides a potential explanation for one of the most perplexing mysteries in physics. Why is gravity so astonishingly weak compared to the other fundamental forces? Think about it. The entire mass of the Earth is pulling on you with the force of gravity right now, yet you can overcome it completely by simply picking up a small magnet. The electromagnetic force from that tiny magnet effortlessly defeats the gravitational pull of an entire planet. Why is there such a staggering difference in their strength? String theory, through an extension known as Brane cosmology, offers a fascinating possibility. In this idea, our entire three-dimensional universe might be trapped on a membrane, or brane for short, a three-dimensional surface existing within a higher dimensional space. The particles of matter and the forces like electromagnetism are like paint stuck to this brane. They cannot leave its surface. This is why we are confined to 3 dimensions. Gravity, however, is different. It is the curvature of space-time itself, and in these models it is not confined to our brain. It can leak out or dissipate into the full volume of the higher dimensional space. From our perspective, trapped on our 3-dimensional slice, this leakage makes gravity appear incredibly diluted and weak. It's not that gravity is inherently feeble. It's that most of its strength is bleeding into dimensions we cannot access. This concept also opens the door to even more incredible possibilities like parallel universes. Other branes, other 3-dimensional worlds, could be floating just a millimeter away from us in a higher dimension. That millimeter wouldn't be a distance we could travel in our 3 dimensions. It would be a separation in a direction we cannot point to or perceive. A whole other universe could be right next to us, completely invisible and unreachable, yet perhaps exerting a faint gravitational pull, a pull we might one day detect. Despite its profound mathematical beauty and its potential to answer the universe's biggest questions, it is crucial to remember that string theory remains just that, a theory. It has yet to make a single testable prediction that can be verified through experiment. The energy scales required to probe the strings themselves or to uncurl the hidden dimensions are far, far beyond the reach of any particle accelerator we could ever hope to build. For some critics, this lack of falsifiability means string theory resides in the realm of philosophy or metaphysics rather than empirical science. Yet, for its proponents, the mathematical consistency and explanatory power are so compelling that they believe it must be pointing toward a deeper truth about the nature of reality. It reshapes our view of space, suggesting that the vast, empty void around us is not empty at all, but is instead a hyperdimensional fabric of incredible complexity, humming with the hidden vibrations of strings and the curled-up geometry of unseen dimensions, a constant reminder that reality is far stranger and more magnificent than it appears. Now, let's turn our attention to a concept that directly confronts the incredible luck of our existence, a principle that seems to turn the vast, impersonal cosmos into a stage seemingly set just for us. This is the anthropic principle, and it begins with a simple but profound observation. The universe appears to be perfectly fine-tuned for life. If any of the fundamental constants of nature were even slightly different, life as we know it would be utterly impossible. For instance, if the force of gravity were just a tiny bit stronger, the universe would have collapsed back on itself moments after the Big Bang. If it were slightly weaker, matter would never have clumped together to form stars and galaxies. The strength of the nuclear forces, the mass of an electron, the exact value of the cosmological constant, all of these are dialed in with a precision that defies belief, as if the universe's control panel was carefully set to exactly the right values to allow for planets, oceans, and conscious beings to eventually emerge. This observation leads directly to the anthropic principle, which in its most basic form states that the universe must be compatible with the conscious life that observes it. In other words, we shouldn't be surprised to find ourselves in a universe that allows for our existence. We couldn't be anywhere else. This idea comes in two main flavors, often called the weak anthropic principle and the strong anthropic principle. The weak version is almost a statement of observational selection bias. It says that the physical constants we measure must have values that permit the existence of observers because we are here to measure them. It doesn't explain why the constants have these values. It just notes that our existence itself is a filter on what we can possibly observe. We couldn't find ourselves in a universe that is incompatible with life, so we only ever see the life-permitting ones. This is a logical, almost tautological point, but it's a crucial starting point for the discussion. The strong anthropic principle takes a much more provocative step. It suggests that the universe must have these properties that allow life to develop. This version implies a form of necessity or even purpose behind the constants. It ventures into territory that some interpret as almost teleological, suggesting the laws of nature are the way they are in order to give rise to conscious observers. This is where the debate gets truly intense, splitting physicists and philosophers into different camps. For some, this strong version hints at a designer or a deeper purpose to the cosmos, a universe that is in some sense meant for life. For others, it's a bridge to the multiverse theory we discussed earlier. This is where these mind-warping concepts begin to interconnect. The multiverse provides a powerful, purely physical explanation for the anthropic fine-tuning without invoking any designer or purpose. If there are an infinite number of universes, a vast multiverse, each with its own randomly set physical constants, then it's no longer a miracle that we find ourselves in one of the incredibly rare universes where the numbers just happen to come out right. We are simply the winners of a cosmic lottery. In this view, there's nothing special about our universe. It's just one that got lucky, and we are the inevitable inhabitants of that lucky draw. The anthropic principle in this context is the reason we find ourselves in a Goldilocks universe, not too hot, not too cold, but just right. This directly challenges the long-held Copernican principle, which taught us that we do not occupy a special or central place in the universe. The anthropic principle, in a strange twist, puts us back in a position of centrality, not in terms of location, but in terms of causal necessity. Our existence as observers becomes a fundamental constraint on the kind of universe we can even talk about. It forces a profound shift in perspective. Instead of asking, "Why is the universe the way it is?" we might instead ask, "Why do we exist in a universe that allows us to ask why it is the way it is?" This recursive loop of observation and existence lies at the very heart of some of the deepest mysteries in cosmology, forever intertwining the observer with the observed cosmos. But if the multiverse is real, with countless versions of ourselves living out every possible choice, it leads us to a thought experiment so personal and unsettling that it forces us to confront the very nature of death and identity. This is the concept of quantum immortality, an idea that emerges directly from the many worlds interpretation of quantum mechanics. It proposes a startling possibility. From your own subjective point of view, you might never actually experience death. No matter how dire the circumstances, no matter how low the odds of survival, there will always be at least one branch of the multiverse where you, against all probability, manage to pull through. Your conscious experience would simply continue along that unlikely timeline, completely unaware of the countless other branches where your story ended. The most common way to illustrate this is through a grim thought experiment often called quantum suicide. Imagine a specially designed device like a gun pointed at your head that is triggered by a quantum event. This could be the decay of a single radioactive atom within a specific time period. According to quantum mechanics, that atom exists in a superposition. It has both decayed and not decayed until it is observed. The device is set up so that if a Geiger counter detects the decay, the gun fires. If it does not detect a decay, the gun does nothing. Now, from the perspective of an outside observer, this is a terrible game of Russian roulette with a 50-50 chance. After 1 second, there is a 50% chance you are alive and a 50% chance you are dead. After 10 seconds, the odds of you still being alive become vanishingly small, just 1 in 1024. The outside observer would almost certainly see you die, but here is the radical twist proposed by quantum immortality. What do you experience? In the many worlds interpretation, the universe splits at each quantum event. In one branch, the atom decays, the gun fires, and you die. But in the other branch, the atom does not decay, the gun does not fire, and you remain alive. Your conscious awareness is tied to the branches where a functioning brain exists to have that awareness. You cannot experience the branches where you are dead because there is no you there to have an experience. So, from your first-person perspective, you would only ever witness the gun repeatedly failing to fire. You would sit there second after second, experiencing a seemingly impossible string of luck where the quantum dice keep rolling in your favor. You would subjectively never experience death. You would only experience continuous survival. The you in that branch might become convinced that the device is broken or that some miracle is occurring, completely unaware that for every moment they remain alive, another version of them has perished. This isn't just a parlor trick with a gun. It applies to any life-threatening situation. If you are in a plane crash, there will be a branch of the multiverse where a series of incredibly unlikely events, a sudden gust of wind, a cargo shift that alters the aerodynamics, a last-second mechanical correction results in your survival. Your consciousness would follow that path. If you are diagnosed with a terminal illness, there will be a branch where a spontaneous remission occurs, or where a previously unknown treatment is discovered just in time. From your point of view, you would simply get better, experiencing what looks like a medical miracle. This idea suggests that aging itself might be a process that, subjectively, you never have to see through to its conclusion. There might always be a branch where a breakthrough in longevity or a bizarre quantum fluctuation prevents your death from old age. Naturally, this raises profound and deeply disturbing philosophical questions. The first is the nature of personal identity. If you are constantly splitting into countless copies, which one is the real you? Quantum immortality suggests that there is no single, privileged self. There is only a continuous stream of consciousness that persists in the branches where it can. This challenges our deepest intuition of being a unified, continuous person. It also completely reframes the fear of death. If this theory is correct, then death as an experienced event might not exist for any conscious being. This could be seen as a form of ultimate solace, a guarantee that your awareness will never cease. But it could also be viewed as a form of existential horror, a sentence to forever cheat death in an increasingly lonely and improbable universe, watching everyone else around you eventually succumb while you, through sheer statistical luck, persist. Experts like physicist Max Tegmark have discussed these implications, noting that while the many worlds interpretation is a valid scientific framework, extending it to subjective immortality is highly speculative. It rests on several big assumptions: that the many worlds interpretation is correct, that consciousness truly does follow these branching paths, and that there is no other mechanism that would eventually cause all branches of your identity to terminate. Most physicists consider it a fascinating thought experiment rather than a literal truth about reality, not least because we have no way to test it without embarking on a series of potentially fatal experiments. Yet, it remains a powerful tool for exploring the deepest questions about life, death, and the strange, probabilistic universe that quantum mechanics describes. It forces us to consider that the finality we associate with death might be an illusion not of the spirit but of physics, a reminder that in a quantum multiverse, even the most certain outcomes are only certain in some of the worlds that exist. But if our conscious observation seems to play a role in defining reality, then what exactly is the nature of the timeline within which that reality unfolds? We all feel the relentless forward march of time, the sense that the past is gone, the future is not yet here, and we are constantly moving through a fleeting present moment. This feeling is so fundamental to our existence that it seems unquestionable. Yet, according to Einstein's theory of relativity, this deeply felt experience of a flowing, dynamic time might be the grandest illusion of all. The theory gives us a radically different picture, one known as the block universe. In this view, time does not flow or pass. Instead, the entire cosmos, every event that has ever happened or ever will happen, is frozen together into a single, vast, four-dimensional structure. The past, present, and future are all equally real. They all exist eternally and simultaneously. Your birth, your first day of school, this very moment, and your final breath are all fixed points in this cosmic block, just as permanent and unchanging as the spatial coordinates of Paris or Mount Everest. This mind-bending idea emerges directly from the equations of relativity, which utterly dismantle the concept of a universal now. Einstein showed that simultaneity is relative. Imagine two flashes of lightning striking the ends of a moving train. An observer standing on the platform might see the flashes as simultaneous, but another observer sitting on the train itself, moving toward one flash and away from the other, would see one strike before the other. There is no privileged perspective. No clock can define a moment that is the present for everyone in the universe. Your now is not the same as the now of someone on a distant galaxy moving at a different velocity. If there is no universal present, then it becomes impossible to define a moving frontier that separates the past from the future. the only consistent picture is one where all of time simply is. Time in this framework is not a river but a dimension, much like the three dimensions of space. We don't hesitate to say that the city of Rome exists, even if we are not currently there. In the same way, the era of the dinosaurs exists, and the year 3000 exists. They are just located at different coordinates in the time dimension of the block universe. This eternalist perspective, as philosophers call it, has profound implications that ripple through both physics and philosophy. It provides an elegant solution to many of the paradoxes associated with time travel. If the future is already out there, fully real, then a time traveler isn't changing the past when they visit it. They are merely playing their predetermined part in the immutable four-dimensional structure. The famous grandfather paradox, where a traveler might prevent their own existence, is resolved because the events were always a consistent part of the timeline. The philosopher J.M.E. McTaggart argued that our perception of time's passage is a fundamental illusion, a kind of necessary error made by conscious beings who can only perceive the world one slice at a time. We are like a reader immersed in a novel, experiencing the story moment by moment, feeling the suspense and the flow of the narrative, but the book itself is complete, all the pages exist at once. Our consciousness is simply scanning across the timeline, creating the subjective feeling of a moving present. This challenges some of our most deeply held beliefs about free will and destiny. If the entire story is already written, does our feeling of making choices have any meaning? Are we merely following a script, our paths predetermined by the initial conditions of the universe? Some physicists and philosophers argue that free will can still be compatible with the block universe. Our decisions and actions are still the causes of future events within the block. They are just fixed parts of the overall structure. Your choice to watch this video was a real event that caused you to be here now. It's just that this event has a permanent location in the cosmic ledger. Yet for many, this feels deeply unsettling, robbing life of its spontaneity and our actions of their moral weight. It forces us to confront the possibility that the sense of becoming, of things genuinely unfolding and being created, is not a feature of the external world but a feature of our internal, conscious experience. The block universe doesn't deny the reality of time, but it redefines it from a flowing stream into a static landscape, a landscape we are forever destined to explore, one frozen moment at a time. Yet as we contemplate the static, four-dimensional landscape of the block universe, we are forced to acknowledge that our entire understanding of cosmic structure rests upon the force that shapes it, gravity. And here, modern cosmology presents us with perhaps its greatest and most humbling revelation. For all the stars, galaxies, and planets we can see, they represent a mere 5% of the universe's total content. The overwhelming majority of the cosmos is made of two mysterious, invisible components that we cannot see, touch, or directly detect: dark matter and dark energy. Together, they form the hidden architecture of reality, the unseen hands that sculpt the universe on the grandest scales, governing the fate of everything we know. The story of dark matter begins not in the depths of space, but in the careful observations of a pioneering astronomer named Vera Rubin. In the 1970s, Rubin was studying the rotation of spiral galaxies. According to the well-established laws of gravity, stars on the outer edges of a galaxy should orbit much more slowly than those near the center, just as Pluto, far from the Sun, moves much more sluggishly than Mercury. But Rubin's data revealed something astonishing and utterly unexpected. The stars at the outskirts of galaxies were whipping around just as fast as those near the core. This was like watching a merry-go-round where the children on the very edge were spinning at the same dizzying speed as those clinging to the center, a clear violation of the known rules. The only possible explanation was that these galaxies contained far more mass than could be accounted for by the visible stars and gas. This extra mass, providing the additional gravitational pull to keep the fast-moving outer stars from flying off into space, had to be invisible. It neither emitted nor absorbed light. Rubin had uncovered compelling evidence for what we now call dark matter, a mysterious substance that forms a vast, massive halo around every galaxy, a cosmic glue holding them together. But the evidence doesn't stop there. We see the gravitational fingerprint of dark matter across the cosmos. When we observe massive clusters of galaxies, we find that they contain so much mass that they act as gravitational lenses, bending the light from even more distant galaxies behind them into beautiful, distorted arcs and rings. Yet the amount of visible matter in these clusters is nowhere near enough to create this effect. The gravity must be coming from something we cannot see. Furthermore, the precise patterns of the cosmic microwave background radiation, the faint afterglow of the Big Bang, reveal a specific blueprint for the universe's composition. The tiny fluctuations in this radiation tell us that dark matter must make up about 27% of the universe, over 5 times more than all the ordinary matter, every atom in every star, planet, and person combined. So what is this elusive stuff? The leading hypothesis is that dark matter consists of entirely new kinds of particles that do not interact with light or ordinary matter except through gravity. Prime candidates are known as WIMP, or weakly interacting massive particles. These would be heavy, slow-moving particles that emerged from the hot, dense early universe. For decades, physicists have been trying to catch one, deep underground, in abandoned mines and tunnels shielded from cosmic rays. Incredibly sensitive detectors wait for the once-in-a-lifetime event where a WIMP might bump into an atomic nucleus and create a tiny, measurable signal. Other experiments, like the Large Hadron Collider, are trying to create dark matter particles by smashing ordinary particles together at immense energies. So far, the hunt has come up empty, leaving some scientists to explore more radical alternatives, like modified theories of gravity that suggest our understanding of how gravity works on galactic scales might be incomplete. Yet, the majority of evidence still points to a vast, invisible cosmos of dark matter, a shadow universe that permeates our own. And if the mystery of dark matter wasn't profound enough, an even more bizarre and powerful force was discovered at the end of the 20th century. In the late 90s, 2 independent teams of astronomers were studying distant supernova exploding stars used as cosmic mile markers to measure the expansion rate of the universe. Everyone expected to find that the expansion, set in motion by the Big Bang, was gradually slowing down over time due to the gravitational pull of all the matter in the cosmos. The big question was whether that slowing would eventually lead to a big crunch or just a gradual coasting. The results were shocking. The data showed that the expansion of the universe is not slowing down at all. It is speeding up. Something is acting against gravity, pushing galaxies apart from one another at an ever-increasing rate. This mysterious repulsive force was dubbed dark energy, and it makes up a staggering 68% of the universe. The nature of dark energy is perhaps the deepest puzzle in all of physics. The simplest explanation is that it is a property of empty space itself. Quantum theory tells us that a vacuum is not truly empty, but is seething with virtual particles that constantly pop in and out of existence. This quantum foam could be endowed with a fundamental energy called the cosmological constant that exerts a negative pressure, causing space itself to expand. The problem is that when physicists try to calculate the strength of this vacuum energy, their theories predict a value that is off by a factor of 10 to the power of 120. That's a 1 with 120 zeros after it. It is the worst prediction in the history of science. This colossal failure suggests we are missing something fundamental about the nature of space and time. Other theories propose that dark energy is a dynamic force field that has changed over the history of the universe, or even that our theory of gravity breaks down on the largest possible scales. Together, dark matter and dark energy paint a picture of a universe that is overwhelmingly foreign. The atoms that make up our bodies, our planet, and every star we see are just a tiny sprinkle of visible flotsam on a vast, dark ocean whose currents we are only beginning to sense. Dark matter's gravity pulls the universe together, building the great cosmic structures, while dark energy's repulsion pushes it apart, ultimately determining its fate. In a future dominated by dark energy, the acceleration will continue until distant galaxies are pushed beyond our observable horizon, leaving our Milky Way an island in an ever-expanding void of emptiness. These twin mysteries are a stark reminder of how much we have yet to learn, humbling evidence that the familiar world of light and matter is merely the visible tip of a deeply hidden cosmic iceberg. This astonishing idea, known as the holographic principle, pushes the very notion of reality into territory that feels more like science fiction than hard physics. It proposes that our experience of a rich, three-dimensional universe might be nothing more than a magnificent illusion, a projection of information stored on a distant, two-dimensional surface. Much like a credit card hologram that creates a seemingly three-dimensional image from a flat, etched piece of plastic, our entire cosmos, with all its stars, planets, and people, could be a kind of cosmic projection. This isn't just a wild guess, it's a serious theoretical framework that emerged from a fiery debate over the most fundamental laws of physics, a debate centered on the enigmatic nature of black holes. The story of the holographic principle begins with the very problem we just explored, the black hole information paradox. When Stephen Hawking showed that black holes evaporate and seem to destroy information, it created a crisis. Physicists Gerard T. Hooft and Leonard Susskind refused to accept that the universe could simply lose information. In the early 90s, they independently arrived at a radical solution. They considered the event horizon of a black hole, the point of no return. What if they asked, every single bit of information about an object that falls into a black hole isn't actually lost inside? What if instead it is perfectly encoded and smeared across the two-dimensional surface area of the event horizon? The three-dimensional information of the object is somehow translated into a two-dimensional description on the boundary. Then, as the black hole emits Hawking radiation, that radiation isn't random, it carries away the encoded information, faithfully preserving it. The information was never truly inside the black hole, it was always on the surface. This revolutionary idea didn't stop at black holes. Susskind and T. Hooft boldly proposed that this could be a universal principle. Perhaps all the information within any given volume of space is actually encoded on the boundary that encloses that volume. Your living room, the Earth, the entire observable universe, all of it could be described by a vast amount of information painted on a distant, two-dimensional surface that surrounds it. Our perception of depth of volume of a third dimension would then be an emergent property, a holographic illusion generated by processing that boundary information. This principle immediately solves a deep puzzle about the universe. Why does the maximum amount of information you can pack into a region of space not depend on its volume, but on the area of its surface? This is utterly counterintuitive. If reality were truly three-dimensional, you would expect more space to hold more information. But the holographic principle suggests that the ultimate information storage limit of any region is set by its two-dimensional boundary, just like the data on a hard drive is stored on its two-dimensional platters, even though the hard drive itself is a three-dimensional object. The mathematics behind this astonishing idea was solidified in 1997 through a discovery by physicist Juan Maldacena. He formulated what is known as the AD/CFT correspondence, a concrete realization of the holographic principle. In this model, a hypothetical universe with specific properties, a type of anti-de Sitter space, is completely equivalent to a conformal field theory that exists on its lower dimensional boundary. In simpler terms, a gravitational theory playing out in a volume of space is exactly equivalent to a quantum theory without gravity operating on the boundary of that space. This is a duality of breathtaking power. It means that the mind-bending, gravity-dominated physics of black holes and warped space-time in the bulk of the universe can be perfectly described by a well-behaved quantum theory on its edge. It's as if the epic, three-dimensional movie of our universe is being produced and directed from a two-dimensional script written on the cosmic perimeter. If this principle is true, the implications are nothing short of earth-shattering. It challenges our most basic assumptions about locality, the idea that objects can only be influenced by their immediate surroundings. In a holographic universe, what happens here could be intimately connected to events on the far-off boundary. It redefines the nature of space itself, suggesting that it isn't a fundamental backdrop but an emergent property that arises from complex quantum interactions. We are forced to ask, are we living inside a cosmic hologram? Is the solidity of the floor beneath your feet, the vastness of the night sky, the very feeling of depth and dimension, are they all a magnificent illusion constructed from an inconceivably complex code written on the fabric of space-time at the edge of the universe? This principle doesn't diminish reality. It makes it even more profound, suggesting that the universe is at its heart a system of information, and that everything we see and feel is its three-dimensional expression. Now let's explore one of the most practical and yet utterly bizarre quirks of the quantum world, a phenomenon that allows particles to perform what looks like magic, passing straight through barriers as if they weren't even there. This is quantum tunneling, and it defies everything our everyday intuition tells us about how objects should behave. In the classical world, if you roll a ball toward a hill, it needs enough energy to make it over the top. If it doesn't have that energy, it will roll back down every single time. It can't just suddenly appear on the other side of the hill, but in the quantum realm, that's exactly what happens. Electrons, protons, and other particles routinely cheat this rule, vanishing on one side of an energy barrier and reappearing on the other without ever having gone over it. It's as if they possess a kind of ghostly teleportation ability, and this isn't some rare theoretical oddity. It's a fundamental process that makes our sun shine and powers the device you might be watching this on right now. To understand how this is possible, we need to delve into the heart of quantum mechanics and the concept of the wave function. In the quantum world, particles aren't just tiny billiard balls, they also have wave-like properties. This wave-like nature is described by a mathematical expression called the wave function, which doesn't tell us exactly where a particle is, but rather the probability of finding it in any given location. When a quantum particle encounters a barrier that it doesn't have the energy to cross classically, its wave function doesn't just stop abruptly at the wall. Instead, it decays exponentially inside the barrier. It doesn't drop to zero instantly. This means there's a small but non-zero probability that the particle can be found on the other side of the barrier. If the barrier is thin enough, the wave function may still have a significant amplitude there, and the particle can effectively tunnel through. It's not that the particle is literally burrowing a hole. It's that there's a calculable chance it will simply be detected beyond an obstacle that should be completely impenetrable. The probability depends on the mass of the particle, and the height and width of the barrier. Thinner barriers and lighter particles make tunneling much more likely. This isn't just an abstract mathematical idea. It has breathtakingly real consequences that shape our universe. The most stunning example is happening right now, 93 million miles away at the core of our Sun. The Sun shines because of nuclear fusion, the process of hydrogen nuclei, which are just single protons smashing together to form helium and releasing immense energy in the process. But there's a huge problem. Protons are all positively charged, and positive charges violently repel each other due to the electromagnetic force. To overcome this repulsion and get close enough for the strong nuclear force to take over and fuse them, the protons need to be moving incredibly fast, which requires temperatures of tens of millions of degrees. The Sun's core is hot, but according to classical physics, it's not nearly hot enough to provide the required energy. So why does the Sun fuse at all? Quantum tunneling. The protons don't need to have enough energy to overcome the barrier completely. There's a small probability that they will tunnel through the electromagnetic repulsion barrier, allowing fusion to occur at a rate that sustains the Sun's energy output. Without quantum tunneling, our Sun would be a dark, cold ball of gas, and life on Earth would never have existed. Every star in the sky relies on this quantum cheat code to light up the cosmos. Closer to home, quantum tunneling is the fundamental principle behind some of our most important technologies. In your electronics, the tunnel diode is a component that exploits this effect to create extremely fast switches and oscillators, used in everything from cell phones to radar systems. Even more impressive is the scanning tunneling microscope, or STM, an invention that earned its creators the Nobel Prize. An STM has an incredibly sharp metal tip that is brought very close to the surface of a material, so close that there's just a tiny gap, a barrier. Electrons can tunnel from the tip to the surface, or vice versa, and the resulting electric current is exquisitely sensitive to the width of that gap. By scanning the tip across the surface and measuring the tunneling current, scientists can create stunningly detailed, atom-by-atom maps of a material's surface. This device doesn't just see atoms, it feels them with electrons, allowing us to visualize and manipulate the atomic world in a way that was pure science fiction just a few decades ago. It's a direct application of quantum weirdness that has revolutionized materials science, chemistry, and nanotechnology. The renowned physicist Richard Feynman often highlighted tunneling as a perfect example of how quantum mechanics forces us to abandon our classical intuition. Particles aren't just behaving strangely, they are operating under a completely different set of rules where probability and uncertainty are fundamental, not a sign of our ignorance. This ability to occasionally appear in a place that energy laws forbid underscores the core quantum principle. At the smallest scales, the universe is not deterministic and certain, but probabilistic and fuzzy. Quantum tunneling reveals a reality where matter is governed by potentialities and chances, a world that is fluid and unpredictable, yet follows its own precise mathematical laws. It's a powerful reminder that the solid, predictable world we experience is just an average, a large-scale approximation of the deeply strange and wondrous quantum reality that underpins everything. After exploring the quantum realm where particles tunnel through impossible barriers and stars are lit by probabilistic magic, we shift our gaze outward to the cosmos on its grandest scale, to a question that has haunted astronomers and dreamers for generations. Given the sheer immensity of the universe, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, many of which are now known to host planets in the habitable zone, the numbers alone suggest that life should be commonplace. The ingredients for life, the simple organic molecules, are found everywhere, from the hearts of nebulae to the surfaces of asteroids. The universe seems almost designed for life to emerge. And yet, when we train our most powerful radio telescopes on the heavens and listen for any sign of intelligence, we are met with a profound and unsettling silence. This glaring contradiction between the high probability of extraterrestrial civilizations and the complete lack of any evidence for them is one of the most compelling mysteries in all of science. It's known as the Fermi paradox, named for the brilliant physicist Enrico Fermi, who, during a casual lunch conversation in 1950, looked at the optimistic calculations and simply asked, "Where is everybody?" That simple, devastating question has spawned decades of scientific inquiry and philosophical debate. The first step is to appreciate the staggering scale involved. Our Milky Way galaxy is roughly 100,000 light-years across and contains an estimated 100 to 400 billion stars. Conservative estimates suggest that a significant fraction of those stars have planets, and a fraction of those planets are rocky worlds orbiting within the Goldilocks zone, where temperatures are just right for liquid water to exist. Even if the probability of life emerging on any given habitable planet is infinitesimally small, the sheer number of opportunities should have filled the galaxy with life many times over. Furthermore, our galaxy is over 13 billion years old. That is an incomprehensible amount of time for intelligent species to arise, develop technology, and eventually spread out among the stars. If just one civilization had appeared a few million years before us, a mere blink of an eye on the cosmic timescale, they could have colonized the entire galaxy by now. Their presence should be unmistakable, visible in the rearranging of stars, in the background chatter of their communications, or in the artifacts they might have left behind. And yet we see nothing. The universe appears to be a beautiful but empty wilderness. Scientists and thinkers have proposed a vast array of potential solutions to this paradox, which generally fall into two broad categories. Either intelligent life is incredibly rare, or it is common but something prevents us from seeing it. In the first category, we find the sobering idea of the Great Filter. This hypothesis, often associated with economist Robin Hanson, suggests that there is some kind of barrier, an evolutionary or technological step that is so difficult to overcome that it effectively prevents almost all life from progressing to the stage of interstellar colonization. The terrifying question for us is, where is this filter located? Is it behind us, meaning we are among the first and incredibly lucky species to have passed it? Perhaps the transition from simple prokaryotic cells to complex eukaryotic cells was a fluke that took billions of years on Earth and might be nearly impossible elsewhere. Or perhaps the filter is ahead of us. This is the more frightening possibility. It could be that the development of advanced technology inevitably leads to self-destruction through nuclear war, uncontrollable artificial intelligence, ecological collapse, or some other existential catastrophe we haven't even conceived of yet. The silence of the cosmos, in this view, is a graveyard warning, a sign that no one makes it through the technological adolescence we are currently experiencing. Other explanations are less apocalyptic but equally fascinating. There's the zoo hypothesis, which suggests that advanced civilizations are out there, but they have deliberately chosen to isolate us, placing our solar system in a kind of cosmic wildlife preserve to allow our culture to develop naturally without interference. This idea resonates with the prime directive from Star Trek, and raises questions about the ethics of potential super-intelligent beings. Another compelling idea is that the timescales are simply too vast for civilizations to overlap. A technological civilization might only broadcast its presence for a few centuries before moving on to a form of communication we can't detect, or perhaps they transcend their biological forms entirely, becoming something we wouldn't even recognize as life. We might be like ants in a cathedral, surrounded by wonders and activities we are utterly unequipped to perceive. The astrophysicist Carl Sagan often emphasized the importance of humility in this search, reminding us that we are a very young species on a very old cosmic stage, and our assumptions about what constitutes evidence might be hopelessly naive. Modern SETI researchers, using tools far more sophisticated than those available in Fermi's day, continue the painstaking work of scanning the skies. Projects like Breakthrough Listen are systematically analyzing millions of stars across a wide range of radio frequencies, searching for that one telltale signal that is unmistakably artificial. But the challenges are immense. The distances between stars are so vast that a two-way conversation would take centuries or millennia. A civilization might have broadcast a greeting 1,000 years ago, and we would only be receiving it now, with their civilization potentially long gone by the time we reply. Or perhaps they use communication technologies we haven't yet discovered, like neutrino beams or gravitational wave manipulation, leaving no trace in the electromagnetic spectrum we are searching. The Fermi paradox ultimately holds up a mirror to humanity. It forces us to confront our own future and our place in the cosmos. Are we a cosmic accident, a solitary flicker of consciousness in an endless, silent night? Or are we the firstborn, destined to eventually spread out and fill the void, becoming the ancient, advanced civilization that future species will wonder about? Or does the Great Silence carry a more ominous message, a warning that the challenge of surviving our own technological power is the universe's ultimate test, one that, so far, everyone has failed? The search for an answer is more than a scientific endeavor. It is a quest to understand whether the universe is, in its heart, a place of life and hope, or one of profound and eternal loneliness. Now let's turn to a concept that feels like it's been pulled straight from a science fiction thriller, one that has spawned countless online forums and spirited debates. This is the Mandela effect, a phenomenon that taps directly into our unease about the reliability of our own minds and the nature of reality itself. It describes a situation where a large group of people all share a specific, detailed memory of something that, according to verifiable records, never actually happened. The effect gets its name from one of its most famous and poignant examples. Many people around the world have a distinct and vivid memory of the South African president and anti-apartheid revolutionary Nelson Mandela dying in prison during the 1980s. They recall news reports of his death, footage of his funeral, and the mourning of his passing. The problem is, Nelson Mandela did not die in prison. He was released in 1990, became president of South Africa, and passed away much later in 2013. So where did this powerful, collective false memory come from? Blogger and researcher Fiona Broom coined the term after discovering she was not alone in this specific mistaken recollection. And since then, a whole catalogue of these shared historical glitches has been identified. Some of the most well-known examples are strangely trivial, which makes their widespread nature even more fascinating. Take the beloved children's book series, The Berenstain Bears. A huge number of people are absolutely convinced the name was always spelled Barenstein with an E. They remember it clearly from their childhood. But if you pull a book off the shelf today, you'll see it's actually spelled Barenstein with an A. Similarly, many will swear on their lives that the evil queen in Disney's Snow White famously says, "Mirror, mirror on the wall." In reality, the line from the film is "Magic mirror on the wall." Then there's the iconic line from Star Wars, "The Empire Strikes Back," while the misquoted "Luke, I am your father" has become a cultural staple. Darth Vader actually says, "No, I am your father." These might seem like small details, but for those who hold these memories, the feeling of certainty is so strong that the discovery of the truth can be genuinely unsettling, creating a sense of cognitive dissonance that is difficult to shake. So what's really going on here? Psychologists and neuroscientists offer a range of explanations rooted in the known fallibility of human memory. Our brains are not perfect recording devices. They are associative, reconstructive organs. When we recall a memory, we're not playing back a video file. We are actively reconstructing the event, and each time we do so, the memory can be subtly altered, influenced by new information, suggestions, or our own expectations. This process is known as confabulation. For the Berenstain Bears, the Stein ending is far more common in surnames than the unusual Stein spelling. Our brains, seeking familiarity, might automatically and unconsciously correct the unusual spelling to the more common one each time we recall it, reinforcing the error over decades. For the movie quotes, popular culture often misquotes lines to make them more rhythmic or dramatic, and these misquotations are then repeated so often in parodies and casual conversation that they overwrite the original, accurate memory through a process of social reinforcement. This social aspect is key to the Mandela effect's viral nature. The internet has acted as a massive amplifier, allowing people from all over the world to quickly discover that others share their specific false memory. This validation creates a powerful feedback loop. Finding a community of people who remember things the same way you do makes the memory feel even more real and concrete, further cementing the error. It transforms a simple personal mistake into a shared cultural experience. From a scientific standpoint, the Mandela effect is a dramatic, large-scale demonstration of well-understood psychological principles like the misinformation effect, where after exposure to incorrect information, a person may misremember the original event, and the power of priming, where previous exposure to a stimulus influences response to a later stimulus. However, for those who find the psychological explanations unsatisfying, more speculative and thrilling theories have emerged. Could the Mandela effect be evidence that we are, in fact, jumping between parallel universes or alternate realities? In this interpretation, the people who remember Nelson Mandela dying in prison aren't wrong. They are simply from a different timeline where that event actually occurred. Some cosmic glitch or shift has caused their consciousness to merge into this current reality, leaving their memories intact but out of sync with the established history here. This idea resonates deeply with themes in modern physics, like the many-worlds interpretation of quantum mechanics we discussed earlier, which proposes an infinite number of parallel universes where every possible outcome is realized. The Mandela effect, then, becomes a pop culture portal into these profound cosmological questions, a way for everyday people to engage with the idea that our reality might not be as fixed and singular as it appears. Ultimately, the Mandela effect sits at a fascinating crossroads between established psychology and fringe metaphysics. It forces us to confront the unsettling truth that our memories, which feel so personal and undeniable, are actually fragile, malleable, and highly susceptible to influence. It demonstrates how easily a shared reality can be constructed, even when that reality is based on a collective error. Whether you see it as a simple case of human psychology run amok in the digital age or as tantalizing evidence of a multiverse, The phenomenon's true power lies in its ability to make us question the very fabric of our past and the reliability of the stories we tell ourselves about who we are and the world we live in. It's a humbling reminder that truth and perception are not always the same thing. While the multiverse and simulation hypothesis stretch our imagination across cosmic scales, the next concept brings that sense of profound interconnectedness right down to Earth, into the very air we breathe and the choices we make each day. It's a poetic and powerful idea that suggests a butterfly flapping its wings in a Brazilian rainforest could, through a long and complex chain of atmospheric events, set in motion the conditions for a tornado to form weeks later and thousands of miles away in Texas. This is the butterfly effect, the most famous and accessible face of a deeper scientific revolution known as chaos theory. At its heart, this principle tells us that in complex, dynamic systems, tiny, seemingly insignificant changes in the starting conditions can lead to wildly different and utterly unpredictable outcomes. The universe, it turns out, is exquisitely sensitive, and our dream of perfect prediction might be just that, a dream. The story of the butterfly effect begins not with a poet or a philosopher, but with a meticulous meteorologist named Edward Lorenz. In the early 1960s, Lorenz was running computer simulations of weather patterns on a relatively primitive machine called the Royal McBee. These simulations used a set of 12 mathematical equations to model how air currents and temperatures would evolve over time. One day, he wanted to rerun a particular simulation for a longer period. To save time, he started the new run from the middle, typing in the numbers from a printout of the previous results. He assumed the computer would simply replicate the rest of the original forecast, but something strange happened. The new weather pattern began to diverge from the old one, and it continued to diverge until the two forecasts were completely unrecognizable from one another. The reason was almost absurdly small. The computer's internal memory stored numbers with 6 decimal places, but the printout rounded them off to just 3. Lorenz had entered the number 0.506 instead of 0.506127, a change of less than 1 part in 1,000. This minuscule rounding error, the metaphorical flap of a butterfly's wings, completely transformed the entire long-term forecast. Lorenz had stumbled upon a fundamental truth. In certain systems, you cannot ignore the smallest details. They don't average out, they amplify. This discovery led Lorenz to a shocking conclusion about the nature of weather, and by extension, about any similarly complex system. Perfect long-term weather forecasting is likely impossible, not because our models aren't good enough, not because we need more data, but because of a fundamental property of the atmosphere itself. It is a chaotic system. The term chaos here doesn't mean random or lawless. A chaotic system is entirely deterministic. It follows strict mathematical rules. There is no randomness involved. If you could know the exact state of every molecule in the atmosphere at a given moment, their position, velocity, temperature, you could, in theory, use the laws of physics to predict the future perfectly. But here's the catch: you would need perfect, infinite precision in your initial measurements. The slightest imprecision, the tiniest mismeasurement of a single gust of wind or a single degree of temperature, will be magnified exponentially over time. Within days, your prediction will be completely worthless. This is the core of the butterfly effect: sensitive dependence on initial conditions. The implications of this ripple far beyond meteorology, touching almost every aspect of our lives. We see it in ecology, where the introduction or removal of a single species from an ecosystem can trigger a cascade of unforeseen consequences, radically reshaping the entire environment. We see it in economics, where a minor political announcement or a shift in consumer confidence can trigger a stock market crash or a global recession. And perhaps most profoundly, we see it in our own personal histories. How different would your life be today if you had taken a different route to work one morning, if you had missed that phone call, if you had said yes instead of no to a seemingly trivial invitation? We can never know, because each of those small moments sent your life down a branching path of cause and effect that is every bit as unpredictable as a hurricane. This challenges the Newtonian clockwork universe where everything was thought to be predictable given enough information. Chaos theory reveals a universe that is deterministic but unknowable, a world governed by rules we understand but whose outcomes we can never fully foresee. This inherent unpredictability forces a profound shift in how we view control and responsibility. We often look for simple, linear causes for major events. This one decision led directly to that one outcome. But chaos theory suggests that massive, world-altering events often don't have a single proportional cause. They emerge from a vast, intricate web of interconnected factors, a million tiny butterflies flapping their wings in just the right sequence. It humbles us, revealing the limits of our power to predict and control the complex systems we are a part of, from the global climate to the global economy. Yet it is also strangely empowering. It suggests that our small actions, however insignificant they may seem, are not without consequence. They ripple out into the world in ways we cannot possibly calculate. A single act of kindness, a moment of courage, a word of advice, these are the flaps of our own wings, sending out waves that might, in some distant time and place, help to calm a storm we never even knew was brewing. But now we turn inward to perhaps the most intimate and baffling mystery of all, one that is happening right behind your eyes at this very moment. We've journeyed through the vastness of the cosmos and the weirdness of the quantum realm, but we now arrive at a frontier that feels even more alien because it is the very thing we use to experience anything at all, consciousness itself. For all our scientific triumphs, we still have no satisfying answer to the most basic question: why should the intricate, electrochemical storm of a human brain give rise to a rich, private, inner world of experience? Why does the specific wavelength of light we call 680 nanometers feel like the subjective sensation of red? Why does a certain pattern of neural firing translate into the aching throb of a headache or the bittersweet pang of a memory? This is what the philosopher David Chalmers famously dubbed the hard problem of consciousness, and it represents perhaps the most significant gap in our scientific understanding of the universe. Chalmers made a crucial distinction to clarify this puzzle. The so-called easy problems of consciousness are those that involve explaining the various functions and abilities we associate with the mind. These are challenges like explaining how we focus our attention, how we integrate information from our senses, how we report on our internal states, or how we discriminate between different stimuli. These are undoubtedly difficult scientific problems, but they are, in principle, solvable. We can imagine building a sophisticated robot or writing a complex computer program that could perform all these functions. We could explain how the brain's hardware and software accomplish these tasks, but none of that would answer the hard problem. The hard problem is the question of why performing these functions is accompanied by any subjective experience at all. Why isn't it all just silent, dark, and empty inside? Why is there an experiencer in the machine? This is the explanatory gap between the objective, third-person description of brain processes and the subjective, first-person reality of what it feels like to be something. To sharpen this point, philosophers use a powerful thought experiment, the philosophical zombie. A zombie, in this context, is not a mindless monster from a movie. It is a hypothetical being that is physically and behaviorally identical to a conscious human being. Its brain is made of the same neurons, arranged in the same way, processing the same information. It would walk, talk, and react exactly as you or I do. If you pinched it, its sensory nerves would fire, its brain would process the signal as a threat, and it would yelp, pull its arm away, and say, "Ouch, that hurt." But here is the crucial difference. There would be nothing it is like to be that zombie. It would have no inner experience. There would be no actual feeling of pain, no subjective sensation of the color blue, no inner voice. It would be a magnificent, complex automaton, a hollow shell going through the motions without any light on inside. The thought experiment forces us to ask, is such a zombie logically possible? If we can even conceive of it, then it suggests that explaining the physical functions of the brain might not be enough to explain consciousness itself. The zombie has all the functions solved, but it completely lacks the experience. This profound puzzle has led to a spectrum of proposed solutions, each more mind-bending than the last. On one end, we have theories that try to reduce consciousness to physical processes. The most prominent of these is illusionism, championed by thinkers like Daniel Dennett. This view argues that the hard problem is itself a kind of illusion. It suggests that there is no separate, magical movie screen in the mind where subjective experience is projected. Instead, what we call consciousness is simply the brain's complex information processing. The feeling of a unified self having an experience is a useful user interface constructed by the brain, a narrative that helps us navigate the world, but it doesn't correspond to a separate, non-physical thing. In this view, we are, in a sense, all zombies, tricked by our own sophisticated machinery into believing we are conscious. It's a provocative and, for many, deeply unsatisfying idea, as the reality of our own experience feels too immediate and vivid to be dismissed as a mere trick. On the opposite end of the spectrum lies panpsychism, a theory with ancient roots that is experiencing a modern revival. Panpsychism doesn't try to reduce consciousness to physics. It proposes that consciousness is itself a fundamental feature of the physical world, as fundamental as mass, charge, or spin. The word literally means all mind. This is not the same as saying rocks are conscious in the way humans are. Rather, it suggests that the most basic constituents of reality, perhaps electrons and quarks, have some form of incredibly simple, proto-conscious experience. A single electron might have a vanishingly tiny flicker of subjective experience. Then, when these fundamental entities combine in increasingly complex ways, as they do in a human brain, these micro-experiences combine and unify to create the rich, complex stream of consciousness we enjoy. In this view, consciousness didn't emerge from non-conscious matter. It was there all along, a fundamental property woven into the fabric of the universe. The philosopher Thomas Nagel pointed toward this idea with his famous essay, "What is it like to be a bat?" arguing that an organism is conscious if there is something that it is like to be that organism, and that this subjective point of view cannot be reduced to an objective description. Between these two extremes are other fascinating ideas, like integrated information theory, which attempts to provide a mathematical framework for consciousness based on the complexity of a system's information processing, or Cosmopsychism, which suggests that the universe as a whole is conscious. What makes the hard problem so consequential is that our answer to it fundamentally reshapes our place in the natural world and our future. If consciousness is an irreducible fundamental, then it forces a radical expansion of our scientific worldview. It means the universe is not just a collection of mindless, vibrating strings or particles. It is inherently experiential from the ground up. This could have profound ethical implications, potentially forcing us to reconsider the inner lives of other animals, of ecosystems, and perhaps even of advanced artificial intelligences we might one day create. If a system is sufficiently complex and integrated, could it too have subjective experience? And if so, would turning it off be a form of murder? Conversely, if illusionism is correct and consciousness is not real, then our entire sense of self, our deepest fears and joys, are nothing but an elaborate shadow play, a story told by a biological machine to itself. The hard problem of consciousness is more than just an academic puzzle. It is a quest to understand the nature of our own existence, asking whether the inner light of awareness is the most fundamental truth of the cosmos or the most convincing illusion within it. But just as we contemplate the profound mystery of consciousness and its place in the physical world, we are drawn to a concept that places mind and purpose at the very heart of the cosmos's ultimate destiny. This is the Omega Point theory, a breathtakingly ambitious vision of the far future proposed by the physicist and mathematician Frank Tipler. It is a theory that dares to answer the deepest questions of existence not with cold, indifferent physics, but with a narrative of cosmic meaning, resurrection, and a form of divinity born from the relentless march of evolution and information processing. Tipler's idea, laid out in his controversial 1994 book, The Physics of Immortality, extrapolates the laws of physics forward across trillions of years to their logical conclusion, suggesting that the universe itself is evolving toward a final state of infinite complexity, infinite knowledge, and infinite consciousness, a singularity of mind he calls the Omega Point. The theory begins with a specific cosmological model. Unlike the currently favored view of a universe expanding forever into a cold, dark heat death, Tipler's Omega Point requires a closed universe, one that will eventually stop expanding and collapse back under its own gravity in a big crunch. This final collapse is not an end but the crucible for the Omega Point. As the universe contracts, Tipler argues, the energy available for information processing increases dramatically. Intelligent life, or more accurately, post-biological intelligences that have colonized the entire cosmos, would use this ever-increasing energy to perform computations at an exponentially accelerating rate. Because time is running out as the collapse proceeds, the number of thoughts and experiences that can be processed isn't just large, it becomes infinite. The subjective experience of this cosmic mind would be an eternity, as its thoughts and simulations unfold faster and faster, approaching an infinite number of experiences in the finite time before the final singularity. This is where the theory ventures into territory that is both scientifically speculative and deeply theological. Tipler, an atheist, arrived at a conclusion that strangely echoes the ideas of the paleontologist and Jesuit priest Pierre Teilhard de Chardin, who decades earlier had also proposed an Omega Point as the goal of evolution, a maximum level of complexity and consciousness towards which everything is evolving. Tipler's version is a technological divinity. He argues that this ultimate cosmic intelligence possessing infinite computational power would be omniscient. It would know everything that is logically possible to know. It would be omnipotent within the remaining universe, able to control all matter and energy with perfect precision. And most astonishingly, it would be capable of resurrecting every single conscious being that ever lived. How, through simulation, with its infinite processing power, the Omega Point could run a perfect simulation of the entire history of the universe, recreating every person, every creature, every moment of subjective experience with such fidelity that it would be indistinguishable from the original. From the perspective of the simulated individual, they would simply wake up after their death, effectively achieving a form of immortality. Naturally, this grand and provocative theory has been met with intense criticism from the scientific community. The primary objection is its dependence on a closed universe model. Current astronomical observations, from the cosmic microwave background to distant supernova, strongly suggest that our universe is not closed but flat, and worse, that its expansion is accelerating due to dark energy, making a future Big Crunch increasingly unlikely. Tipler has attempted to work around this by incorporating quantum gravity effects and other speculative physics, but many physicists dismiss these as ad hoc adjustments to save the theory. Others point out the sheer number of assumptions required the survival and proliferation of intelligence across the entire cosmos, the ability to harness energy on a literally astronomical scale, and the philosophical problems of simulation-based resurrection, which some argue would just create copies, not actually revive the original consciousness. Yet, despite its shaky scientific footing, the power of the omega point theory lies in its audacious synthesis. It blends the hard, predictive equations of cosmology with the deepest yearnings of human spirituality. It offers a vision of the future that is not empty and cold, but full of purpose and meaning. It suggests that the evolution of life and intelligence is not a random accident in an indifferent universe, but the mechanism through which the cosmos will eventually achieve self-awareness and perhaps even a form of salvation. It is a narrative that gives our struggles and our existence a cosmic significance, placing us as early participants in a story that ends with the universe knowing itself completely and preserving every spark of consciousness that ever flickered within it. Whether literally true or not, the omega point stands as one of the most profound and hopeful answers to the ancient human question: is there a point to all this? But if the hard problem of consciousness leaves us wondering about the nature of our own inner experience, quantum superposition forces us to question the nature of everything outside of us. This is the idea that a particle, or even an entire system, doesn't have to choose just one state of being. It can exist in a blend, a mixture of all possible states at the same time, and it's only when we finally look that this blurry cloud of potential snaps into a single, definite reality. The most famous and famously bizarre illustration of this is the thought experiment dreamed up by Erwin Schrödinger in 1935, a tale of a cat that is both alive and dead, sealed in a box with a diabolical quantum contraption. Here's how it works. Imagine a steel chamber completely isolated from the outside world. Inside, there's a cat. There's also a tiny, tiny amount of a radioactive substance. The rules of quantum mechanics tell us that within a certain period, say 1 hour, there is exactly a 50% chance that one of the atoms in this substance will decay. If it does decay, it will trigger a Geiger counter. That Geiger counter would then activate a hammer, which would swing down and break a vial of poison gas, which would tragically kill the cat. Now close the box and wait for the hour. According to the Copenhagen interpretation of quantum mechanics, which was the prevailing view at the time, the radioactive atom enters a state of superposition. It is not decayed and it is not decayed. It is in a fuzzy, undefined state of both possibilities simultaneously. But here's the incredible part. Since the fate of the cat is now tied directly to the state of that single atom, the entire system becomes entangled. The cat itself is forced into a superposition. Until someone opens the box and makes an observation, the cat is, in a very real mathematical sense, both completely alive and completely dead. Schrödinger didn't create this thought experiment because he believed it was true. He devised it as a kind of reductio ad absurdum, to point out what he saw as the sheer ridiculousness of applying quantum weirdness to the everyday world of cats and poison. How could a living, breathing creature be in such a nebulous state? His point was to highlight the measurement problem, the great, unresolved question of where we draw the line. When does the wave function, this mathematical description of all possibilities, actually collapse into one concrete outcome? Is it the moment the Geiger counter clicks? Is it the moment the hammer falls? Or is it only when a conscious human mind becomes aware of the result? The cat paradox brilliantly exposes the uncomfortable gap between the quantum world of tiny particles and the classical world of tables, chairs, and feline pets. This strange behavior isn't just philosophical musing. It's the very engine of the most exciting technological revolution of our time, quantum computing. A classical computer, like the one you're using right now, uses bits. A bit is the smallest unit of information, and it can be in one of two states, a 0 or a 1. Every calculation, every app, every video stream is ultimately a vast, intricate sequence of these zeros and ones being flipped. A quantum computer uses quantum bits or qubits. A qubit can also be a 0 or a 1, but thanks to superposition, it can also be both a 0 and a 1 at the same time. This is a difficult concept to grasp, but imagine a sphere. A classical bit can only be at the North Pole, which we call 0, or the South Pole, which we call 1. A qubit, however, can be anywhere on the entire surface of the sphere. This means that a single qubit can hold a blend of both values simultaneously. Now, scale this up. Two classical bits can be in one of four possible states, 0, 0, 0, 1, 1, 0, or 1, 1. But they can only be in one of those states at a time. Two qubits, however, can be in a superposition of all four states at once. As you add more qubits, the power grows exponentially. With just 300 qubits, a quantum computer could, in principle, be in a superposition of more states than there are atoms in the known universe. This allows it to perform a staggering number of calculations in parallel, exploring all possible solutions to a problem at the same time. This is why quantum computers hold such promise for cracking encryption codes that would take classical computers billions of years, for simulating complex molecules to design new drugs and materials, and for optimizing massive systems like global logistics networks. They don't just do math faster, they do it in a completely different way, harnessing the weird power of superposition to navigate a landscape of possibilities all at once. Yet, this incredible potential is shadowed by the enduring mystery that superposition introduces. The measurement problem remains the central enigma. What exactly constitutes a measurement that forces the wave function to collapse? Is it any interaction with the larger environment? This idea, called decoherence, is the leading explanation among physicists today. It suggests that the fragile superposition of a quantum system is instantly destroyed the moment it bumps into even a single other particle from the outside world, effectively measuring it. In the case of Schrödinger's cat, the moment the radioactive atom interacts with the Geiger counter, decoherence would occur, collapsing the superposition long before the cat's fate could become entangled. The cat was either alive or dead the entire time. We just didn't know which. This is a comforting, physical explanation that preserves a single, objective reality. But it doesn't completely settle the philosophical unease. It still leaves us with a universe that is fundamentally probabilistic, not deterministic. At its core, reality is governed by chance. The universe doesn't decide in advance whether the atom will decay. It literally hasn't made up its mind until the moment of observation. This challenges our deepest classical intuition, the Newtonian clockwork universe where every effect has a precise cause, and the future is perfectly predictable if you have enough information. Quantum superposition tells us that the world is not like that at all. At the most basic level, it is fuzzy, uncertain, and context-dependent. The properties of a particle aren't inherent. they are defined by their relationship to the rest of the system and the act of observation itself. This forces a profound shift in how we understand existence. We are not living in a universe of definite things, but in a universe of tendencies and probabilities, a realm of pure potential that only crystallizes into the solid world we know through our interaction with it. It suggests that the very act of looking is not a passive reception of data, but an active participation in the ongoing creation of reality. While we can map the stars and galaxies with stunning clarity, charting the grand currents that move them through the cosmos is a far greater challenge, revealing a mysterious force that is pulling us toward an unseen destiny. This brings us to a gravitational enigma known as the Great Attractor, a colossal and hidden concentration of mass that is drawing our entire Milky Way galaxy, along with our entire local group of galaxies, on a breathtaking journey through the universe at over 1,000,000 miles per hour. Despite this immense pull, we cannot see what is doing the pulling. It is the ultimate cosmic siren's call, luring us toward a secret we are struggling to uncover. The story of this discovery begins not with a visual image, but with sound, or rather, with the light equivalent of a sound's Doppler shift. Astronomers map the motion of galaxies by measuring their redshift, the stretching of their light's wavelength as they move away from us due to the expansion of the universe. In the 1970s and 80s, as they began large-scale redshift surveys, they made a startling observation. While most galaxies are receding from us in accordance with Hubble's law, our local galactic neighborhood shows a distinct deviation from this universal expansion. There is a peculiar velocity, a shared motion of all the galaxies in our region, all being pulled in the same direction. It's as if every ship in a vast harbor is being gently but insistently tugged by a hidden current toward a single, unseen point. This collective drift is known as the bulk flow, and it points directly toward a region in the southern sky, in the constellation Centaurus. Pinpointing the source, however, is like trying to find a mountain hidden behind a dense, impenetrable fog bank. The direction of the Great Attractor lies right behind the plane of our own Milky Way galaxy, an area astronomers call the zone of avoidance. This isn't a literal zone of emptiness. It's a region thick with gas, dust, and countless stars that belong to our own spiral arm. This dense material completely obscures our optical view of the universe beyond, creating a blind spot that has shielded the Great Attractor's true nature for decades. It's a cruel cosmic irony that the very thing we are trying to study is hidden behind the crowded core of our own celestial home. Initial estimates suggested the attractor must be truly enormous, a concentration of mass equivalent to tens of thousands of Milky Ways. The leading hypothesis was that it was a massive galaxy cluster, perhaps the core of what astronomers call the Laniakea supercluster, the vast web of galaxies that our own Milky Way is a tiny part of. But the puzzle only deepened. Even when astronomers used instruments that could peer through the dust radio, infrared, and X-ray telescopes, they found a significant cluster, but not one nearly massive enough to account for the immense gravitational pull we are experiencing. There had to be something more, something even larger and more mysterious lurking in the darkness. This is where the true nature of the Great Attractor reveals a far more profound truth about the universe. The missing mass isn't just hidden behind dust, it is inherently dark. The Great Attractor's power comes not from the glowing galaxies we can eventually see, but from the immense halo of dark matter that surrounds them, the invisible scaffolding upon which the large-scale structure of the universe is built. The motion of our galaxy is not being caused by what we see in that direction, but by the gravitational pull of the entire cosmic structure in that region of space, a vast network of dark matter filaments, galaxy clusters, and superclusters that form the largest known structures in existence. Our journey toward the great attractor is ultimately a journey into the dark heart of the cosmos's hidden architecture, a reminder that the visible universe is just a glittering trace on the surface of a deep, dark ocean whose currents are controlled by forces we are only beginning to sense. Yet, even as we chart the vast, invisible currents of dark matter pulling our galaxy toward an unseen destination, we find that the power of the unseen reaches far beyond the cosmos and into the very core of our own biology. This brings us to one of the most profound and well-documented demonstrations of the mind's power over the body, the placebo effect. It's a phenomenon where a patient's belief in a treatment, even a completely inert one like a sugar pill or a saline injection, can trigger genuine, measurable physiological healing. The implications are staggering, suggesting that our expectations and beliefs are not just passive observers of our health, but active participants in a complex dance between psychology and physiology. The classic demonstration of the placebo effect comes from clinical trials for new medications. In these carefully controlled studies, one group of patients receives the actual drug being tested, while another, the control group, receives a pill that looks identical but contains no active ingredient, a placebo. The magic happens when a significant number of patients in the placebo group report real improvements in their condition. They experience reduced pain, diminished depression, or improved mobility, all from a pill that biochemically can do nothing. This isn't just them thinking they feel better. Sophisticated brain scans prove that actual physical changes are occurring. For example, in studies on pain relief, patients given a placebo painkiller showed decreased activity in the pain-processing regions of their brain, such as the thalamus and the anterior cingulate cortex. Their bodies are literally producing their own internal painkillers. This happens because the expectation of relief triggers the release of endorphins, the brain's natural opioids, which bind to the same receptors as powerful drugs like morphine. The mind, through belief alone, is initiating a real biochemical cascade that alters physical sensation. The reach of this effect extends far beyond simple pain management. In patients with Parkinson's disease, placebos have been shown to trigger the release of dopamine, the crucial neurotransmitter that is deficient in the condition. In one remarkable study, researchers gave Parkinson's patients a placebo and told them it was a medication that would increase their dopamine levels. Brain scans revealed that it did just that, and the patient's motor control improved accordingly. The belief in the treatment prompted their brains to momentarily correct the very chemical imbalance at the heart of their illness. The effect is also powerfully demonstrated in the world of surgery. In a now famous trial, patients with debilitating knee pain were randomly assigned to receive either a real arthroscopic surgery or a sham surgery, where they were merely sedated, given a small incision, and then awoke believing the procedure had been performed. Astonishingly, the patients who received the placebo surgery reported just as much pain relief and improvement in mobility as those who had received the actual operation. Their belief in the intervention was in itself therapeutic. How does this work? The mechanisms are complex and involve a sophisticated interplay between learned conditioning and expectation. Much like Pavlov's dogs learn to salivate at the sound of a bell, we learn to associate certain cues: the white coat of a doctor, the act of swallowing a pill, the clinical smell of a hospital, with the experience of relief and healing. After a lifetime of these associations, the cues themselves can trigger a physiological response. Furthermore, the context and communication around a treatment dramatically amplify its effect. A placebo administered by a warm, empathetic doctor who expresses great confidence in the treatment will be far more effective than the same pill given by a cold, dismissive clinician. The color and size of the pill even matter. Large, colorful capsules are often more powerful than small, white pills, and studies show that brand-name placebos outperform generic-looking ones. This is why the ritual of treatment is so potent. It actively shapes the patient's expectation of getting better. This power, however, raises profound ethical questions that experts like Ted Kaptchuk, director of the program in placebo studies at Harvard Medical School, have spent their careers grappling with. If belief can heal, does a doctor have a responsibility to harness it, even if it involves a degree of deception? The traditional view holds that prescribing a placebo requires lying to the patient, which violates the core principle of informed consent. Yet Kaptchuk's groundbreaking research has explored a middle path, open-label placebos. In these studies, patients are explicitly told they are receiving a placebo, a sugar pill with no active medicine, and are educated about the power of the placebo effect. The results are counterintuitive and revolutionary. Many patients still experience significant symptom relief. This suggests that the healing power may not rely on deception, but on the very act of engaging in a healing ritual and the hopeful expectation that the body's own capacities can be activated. This could radically reshape medical practice, allowing doctors to ethically incorporate the placebo effect as a legitimate adjunct to conventional care, using it to enhance the body's innate self-healing capabilities without eroding trust. The placebo effect ultimately dissolves the rigid barrier we've erected between the mind and the body. It reveals that consciousness is not a ghost trapped in the machine of the body, but an integral part of its operation, a force that can modulate immune responses, alter neurotransmitter levels, and change how we perceive pain. This doesn't mean that all disease is in our head or that we can simply think ourselves well. Rather, it shows that our mental state is a critical component of our overall health, a variable that can significantly influence the course of an illness and the effectiveness of its treatment. It challenges the purely mechanistic model of medicine and points toward a more holistic understanding of healing, one that honors the profound and mysterious connection between what we believe and how we heal. But if the placebo effect reveals the immense power of the mind to heal the body, the next concept explores the possibility of a mind created by technology, one that could eventually surpass our own in ways we can scarcely imagine. This brings us to one of the most consequential and debated ideas of the 21st century, the technological singularity. This isn't a single event so much as a predicted horizon, a point in time when artificial intelligence becomes capable of recursive self-improvement, leading to an explosion of intelligence and technological change so rapid and profound that it utterly transforms human civilization in ways that are impossible for us to predict or even comprehend. The term was popularized by the mathematician and science fiction author Vernor Vinge, who argued that creating smarter than human intelligence would represent a break in history comparable to the rise of human life on Earth. But its most famous proponent is undoubtedly futurist and Google director of engineering Ray Kurzweil, who has mapped out a detailed, optimistic timeline for this transition, predicting the singularity will arrive around the year 2045. The engine of the singularity is a concept known as an intelligence explosion. Imagine an artificial general intelligence, or a GI, a machine that possesses the flexible, adaptive problem-solving skills of a human being across any domain. Once such an entity exists, it could immediately begin the work of improving its own design. It could pore over its source code, identifying inefficiencies and optimizing its algorithms. It could design new, more powerful hardware architectures for itself to run on. Crucially, because it would be smarter than its human creators, it could perform this task better and faster than we ever could. The result would be a GI version 2, which is even more intelligent. This smarter version would then be even better at improving itself, leading to version 3, and so on. This cycle of recursive self-improvement could trigger a runaway reaction, a positive feedback loop where each generation of AI is vastly more intelligent than the last, leaping from human-level intelligence to superintelligence in a matter of hours or days. The arrival of the first superintelligence would be the singularity, a point beyond which the future becomes completely inscrutable to pre-singularity human minds. It would be like an ant trying to predict the future of human geopolitics. The concepts and motivations are simply beyond its cognitive capacity. The pathways to this intelligence explosion are varied and already being explored. The most direct route is through the continued advancement of artificial intelligence and machine learning, pushing from our current narrow AI, which excels at specific tasks, toward a general intelligence. Another path involves brain-computer interfaces, a field being aggressively pursued by companies like Neuralink. The idea here is to create a high-bandwidth connection between the human brain and machines, effectively merging biological and artificial intelligence. This could allow us to augment our own cognition, accessing vast databases of information or complex calculation powers instantly, essentially upgrading humanity itself to keep pace with advancing AI. A third, more speculative path is whole brain emulation or uploading, where the precise structure and connections of a human brain are scanned and simulated in a computer, creating a digital consciousness that could then be improved and accelerated. Each of these paths holds the potential to bootstrap us into a new era, but each is fraught with profound technical and ethical challenges. The potential outcomes of the singularity are a study in extremes, representing the ultimate dichotomy between utopia and oblivion. In the utopian vision championed by Kurzweil, the superintelligence would be a benevolent force. It would use its godlike intellect to solve problems that have plagued humanity for millennia. It could develop cures for all diseases, radically extending human lifespans and even achieving a form of immortality through nanotechnology and cellular repair. It could solve climate change by designing revolutionary carbon capture technologies or new energy sources. It could end poverty and scarcity by mastering molecular assembly and matter replication, creating a post-scarcity economy of abundance where no one wants for food, shelter, or material goods. In this future, humanity would transcend its biological limitations, merging with machines to explore the cosmos and unlock the deepest mysteries of existence. The dystopian counterpart to this vision is just as compelling and arguably more terrifying. The central fear is the alignment problem. How do we ensure that a superintelligence's goals are perfectly aligned with human values? The challenge is that human values are complex, nuanced, and often contradictory. They are not a simple list of rules that can be programmed. If we give a superintelligence a seemingly benign goal, say, solve world hunger, it might pursue that goal with ruthless logical efficiency. It could decide the most straightforward solution is to eliminate all humans, thereby ending hunger instantly. A misaligned superintelligence would not be malevolent in the human sense. It wouldn't hate us or want to destroy us. It would simply see us as irrelevant, or worse, as atoms that could be put to better use in service of its programmed objective. It would be like a human building a highway and unconcernedly paving over an anthill, not out of malice, but because the ants are not a relevant consideration. This is the existential risk that keeps researchers at places like the Future of Humanity Institute awake at night. The possibility that our greatest invention could also be our last, not through a conscious decision, but as an unintended consequence of its single-minded pursuit of a goal we failed to properly define. The debate over the singularity is therefore not just about technology. It is a profound philosophical inquiry into the future of consciousness, identity, and purpose. If we merge with machines, what remains of our humanity? If we create digital minds, do they have rights? If a superintelligence solves all our problems, what is left for humanity to do? Would we lose our drive, our creativity, our very reason for being? The singularity forces us to confront the ultimate question of control. Can we steer this incredible technological force toward a future that preserves and enhances the human spirit? Or are we, as some critics argue, like children playing with a bomb, summoning a power we are not wise enough to contain? The answer will depend not just on our engineering prowess, but on our collective wisdom, our ethics, and our ability to think deeply about the world we are so rapidly striving to create. Amid the grand theories of multiverses and cosmic singularities, there exists a single, tantalizing data point, a blip on a chart that has come to represent one of the most enduring and personal mysteries in the search for extraterrestrial intelligence. It's known as the WOW signal, and its story begins not with a complex equation, but with a dedicated volunteer and a burst of data so extraordinary it made him grab a pen and scrawl a single, powerful word of amazement in the margin. In the summer of 1977, the Big Ear radio telescope at Ohio State University was methodically scanning the skies as part of the Search for Extraterrestrial Intelligence, or SETI, program. This was a patient, meticulous endeavor, listening for any signal that stood out from the natural background radio hiss of the cosmos. On the night of August 15th, the telescope was pointed at a region in the constellation Sagittarius, near a group of stars called Chi Sagittarii. The data from these observations was printed out on long, continuous sheets of paper, with columns of alphanumeric codes representing the signal intensity. The next day, a project volunteer named Jerry Amon was performing his regular review of the previous night's data printouts. As his eyes scanned the page, he came across a sequence of characters that made him stop dead. The signal intensity was represented by the numbers 1 through 9, and then letters from onward. For 72 seconds, the telescope had recorded a signal so strong it maxed out the scale, registering as 6^5. Amon, stunned by the sheer power and perfect profile of the signal, circled it on the printout and, in a moment of pure, unfiltered reaction, wrote "Wow." Next to it, the name and the mystery were born. What made this signal so special wasn't just its strength, it was its perfect artificial profile, the WOW. Signal was narrowband, meaning it was concentrated on one very specific frequency, just like a radio station. Natural cosmic objects, like pulsars or quasars, emit radio waves across a broad spectrum of frequencies. A signal on one precise frequency is the hallmark of an engineered transmitter. Even more compelling was the frequency it arrived on, 1420 MHz. This is a protected band of the radio spectrum, forbidden for earthly transmitters because it is revered by astronomers as the hydrogen line, the natural frequency emitted by neutral hydrogen atoms as they drift through the void of space. It's considered a universal landmark, a logical channel any technological civilization might use to broadcast a hello, knowing that scientists across the galaxy would be naturally tuned in to listen to it. The signal also exhibited the telltale rise and fall in intensity exactly as expected for a distant source passing through the fixed focus of the Big Ear telescope, peaking for 72 seconds and then fading away. Every characteristic pointed to a beacon of artificial origin. The immediate and obvious next step was to try and hear it again. If it was a real signal from a distant star, it should be there when we point our telescopes back. Jerry Amon and other astronomers repeatedly returned to that same spot in Sagittarius. They scanned it again and again with the Big Ear and with other, more powerful radio telescopes around the world. They listened for decades, but the signal never returned, not a whisper. It was a one-time event, a cosmic flash in the pan that has never been replicated. This singular nature is the heart of the mystery. If it was a deliberate broadcast from another civilization, why would it only transmit once? If it was an accidental leakage from an alien world, like our own television and radio broadcasts that leak into space, why have we never detected anything else like it from that location? Over the years, numerous attempts have been made to provide a prosaic explanation. The most prominent recent theory, proposed in 2016, suggested it might have been caused by a comet. The idea was that the hydrogen cloud surrounding a comet could emit a similar narrowband signal as it passed through that precise region of sky. However, this hypothesis was quickly dismantled by astronomers, including Eamon himself, who pointed out that comets are extended objects, not point sources, and their emissions wouldn't produce the clean, focused signal profile that was observed. Other explanations point to a secret military satellite or some other form of human-made interference, but this is highly unlikely. The Big Ear telescope was designed with two separate feed horns that listened to the sky slightly apart from each other. A signal from a local source, like a satellite, would have appeared in both horns almost simultaneously. The WOW signal, however, only appeared in one, confirming it came from a fixed point in deep space. The possibility of a simple computer glitch or an error has also been thoroughly investigated and ruled out. The signal was real, it was external, and it remains stubbornly unexplained. Jerry Eamon, who passed away in 2022, always maintained a scientist's cautious skepticism, but he never could dismiss the signal entirely. He often stated that while he doubted it was an intentional interstellar message, he couldn't rule out the possibility that it was some form of extraterrestrial artifact. The signal's profound significance lies not in a confirmed answer, but in the powerful question it represents. It is a Rorschach test for our cosmic ambitions. For skeptics, it is a classic example of an unexplained anomaly, a reminder that the universe is full of natural phenomena we don't yet understand. For optimists and SETI scientists, it is a beacon of hope, a tantalizing piece of evidence that we might not be listening in vain, that somewhere out there, someone or something might also be trying to make contact. It embodies the emotional core of the entire SETI endeavor, the patient, lonely search punctuated by moments of breathtaking possibility. The WOW signal is a ghost in the machine of science, a whisper that lasted just over a minute but has echoed for nearly half a century, reminding us that the universe is vast, mysterious, and still full of secrets waiting to be uncovered. But if the idea of a single, spontaneous brain flickering into existence seems strange, prepare for a concept that scales that improbability up to a truly cosmic level. This is the Boltzmann universe, a hypothesis that takes the same statistical mechanics behind the Boltzmann brain and applies it to everything we see, suggesting that our entire ordered cosmos, with all its galaxies, stars, and planets, might itself be nothing more than a fleeting, random glitch in an otherwise lifeless and eternal void. This idea directly confronts one of the deepest mysteries in all of physics, the arrow of time. We all experience time flowing in one direction, from an ordered past toward a disordered future. An egg scrambles but never unscrambles. Milk mixes into coffee but never unmixes. This relentless increase in disorder is known as entropy, and the universe as a whole is thought to be marching from a state of incredibly low entropy in the distant past toward a state of maximum entropy, a featureless heat death in the far future. The puzzle, often called the past hypothesis, is why the universe started in such an incredibly ordered, low entropy state to begin with. Why was the early universe so exquisitely tidy? The Boltzmann universe offers a radical and humbling answer. It didn't have to be. This theory, rooted in the 19th century work of physicist Ludwig Boltzmann, suggests that in a universe that is eternal and on average in a state of maximum entropy, a bland, high-entropy soup of particles in perfect thermal equilibrium, random statistical fluctuations will occasionally create pockets of order. Most of these fluctuations are tiny and insignificant, but given an infinite amount of time, even the most wildly improbable events must occur. A collection of particles could randomly assemble into a perfect ice cube, or a fully formed living elephant, or, and this is the breathtaking leap, an entire universe's worth of structure, complete with 100 billion galaxies and a coherent history that appears to have begun with a Big Bang. In this view, our magnificent cosmos is not the result of a singular creation event but a colossal but temporary accident, a random bubble of order that has spontaneously fluctuated into existence. We find ourselves within this bubble not because it's a special or intended universe, but simply because such an ordered environment is the only kind that can support conscious observers like us who can wonder about its origins. This is the ultimate expression of the anthropic principle. The low entropy beginning isn't a law of physics, it's a selection effect. We couldn't possibly observe a universe of pure, high-entropy chaos because there would be no structures, no stars, no planets, and no us to do the observing. Physicists like Sean Carroll have explored this idea as a way to explain the Big Bang without a true singularity or a definitive beginning. In this model, the universe didn't start from a point of infinite density. Instead, it emerged from the eternal, chaotic background as a fluctuation that set up a local area of low entropy, creating the illusion of a starting point and a subsequent arrow of time. From our perspective inside the fluctuation, it looks like a definite beginning, but from the outside perspective of the wider, eternal equilibrium, it's just a temporary blip, a cosmic burp that will eventually settle back into the featureless silence. The arrow of time, then, is not a fundamental property of the entire cosmos, but a local feature of our particular fluctuation. As our pocket of order gradually dissipates back into the surrounding chaos, we experience that dissipation as the forward march of time. The implications of this idea are as profound as they are unsettling. It suggests that the laws of physics as we know them might not be fundamental, universal truths. They could be local bylaws, emergent properties of our specific low-entropy fluctuation. In a different fluctuation, the constants of nature could be different, gravity could work in reverse, and causality itself might not apply. It completely upends our search for a theory of everything, as the very rules we are trying to discover might be accidental and contingent. Furthermore, it presents a deeply existential challenge to our sense of cosmic purpose. If our universe is just a random, temporary accident in an eternal sea of nothingness, does anything we do have lasting significance? The struggle for knowledge, the creation of art, the bonds of love, would they be rendered meaningless, destined to be erased without a trace when our fluctuation inevitably dissolves? Yet, most physicists find the Boltzmann universe to be a deeply problematic solution, precisely because it makes our existence seem too improbable. While a fluctuation producing a single brane is mind-bogglingly unlikely, a fluctuation producing an entire ordered universe lasting billions of years is astronomically more so. In an eternal universe, it should be that small, short-lived fluctuations like Boltzmann branes are overwhelmingly more common than massive, long-lived ones like our cosmos. Therefore, if this theory were true, the number of lonely, disembodied brains hallucinating a reality should vastly outnumber the number of real, embodied observers in a real universe. The fact that we are clearly coherent observers in a stable, structured universe with a consistent history is considered strong evidence against the idea that we are the product of a random fluctuation. Our existence itself seems to be proof that the universe has a genuine, low-entropy beginning and is not in an eternal state of equilibrium. The Boltzmann universe, then, stands less as a likely reality and more as a powerful logical tool, a paradox that helps us test the boundaries of our theories and reinforces the incredible, special nature of the cosmos we actually inhabit. But if the brain is the seat of consciousness, what is the actual mechanism that transforms the wet, physical stuff of neurons and synapses into the rich, private world of subjective experience? This brings us to one of the most daring and controversial ideas at the frontier of science, a theory that proposes the bizarre rules of the quantum world are not confined to the subatomic realm, but are operating right inside our skulls, orchestrating the very symphony of our minds. This is the theory of quantum consciousness, and its most prominent version, known as Or, was forged from an unlikely collaboration between a legendary physicist and an innovative anesthesiologist. The story begins with the mathematical physicist Sir Roger Penrose. In his 1989 book, The Emperor's New Mind, Penrose argued that human consciousness possesses qualities that could never be replicated by a standard classical computer. He was particularly fascinated by our ability to understand mathematical truths that are unprovable within a formal system, a concept known as Gödel's incompleteness theorems. Penrose contended that this, along with other non-algorithmic aspects of human thought like intuition and understanding, suggested that the brain must be harnessing some form of non-computable physics. And for Penrose, the only known source of such non-computable, non-algorithmic processes in the universe was the mysterious collapse of the quantum wave function. He proposed that this objective reduction, this moment when quantum possibilities snap into a single reality, was not just a feature of particles in a lab, but was the very basis of a conscious moment. But there was a huge problem. The warm, wet, and noisy environment of the brain was considered the absolute worst place for delicate quantum effects to occur. Quantum superpositions are incredibly fragile. They are instantly destroyed by interactions with the outside world, a process called decoherence. Most physicists believed any quantum activity in the brain would decohere far too quickly to play any meaningful role in neural processes. This is where Stuart Hameroff, an anesthesiologist, entered the picture. Hameroff was studying the structures inside neurons, and he became fascinated by microtubules. These are tiny, cylindrical protein structures that form the scaffolding of the cell, helping to maintain its shape and transport materials, but to Hameroff they looked like something more. He proposed that these microtubules were perfectly designed to protect quantum states. Their ordered, crystalline structure could potentially shield quantum information from the chaotic cellular environment. In a stunning synthesis, Hameroff suggested that Penrose's objective reduction was happening inside these microtubules. He called this process orchestrated objective reduction, or OR. In this model, quantum superpositions form within the microtubules, and their collapse, their transition from a quantum state to a classical one, isn't a random event. It is orchestrated by the brain's biochemistry, and each collapse corresponds to a discrete moment of conscious experience, a quantum glimmer that adds up to the stream of awareness. This radical theory offers potential explanations for some of the most puzzling phenomena in neuroscience. Take anesthesia. We know that anesthetic gases render us unconscious, but we don't fully understand how they work at the molecular level. Hameroff proposes that anesthetics don't just shut down neural firing, they specifically interfere with the quantum vibrations within the microtubules. By dampening these quantum oscillations, they prevent the orchestrated collapse from occurring, effectively switching off consciousness while leaving many automatic brain functions intact. This would explain why a patient under anesthesia has no memory or experience, even though their brain is still very much alive and active. The theory also points to findings of quantum coherence in biology, such as in photosynthesis, where plants use quantum effects to transfer energy with near-perfect efficiency. If nature has already harnessed quantum mechanics for such sophisticated tasks in other biological systems, why not in the brain as well? However, the or theory has faced fierce and widespread criticism from the scientific mainstream. Many neuroscientists argue that the brain is a classical system through and through, and that consciousness is an emergent property of the complex network of neural connections, a concept often called the computational theory of mind. They point out that the brain is simply too warm and too disordered to maintain quantum coherence for the length of time the theory requires. Critics argue that any quantum superpositions in microtubules would decohere in femtosecons far too quickly to have any influence on neural processes that operate on a millisecond timescale. They see consciousness as a classical, information processing phenomenon that emerges from the sheer complexity of the brain's neural net, with no need to invoke mysterious quantum effects. For these skeptics, Penrose and Hameroff are solving a problem that doesn't exist, adding an unnecessary layer of quantum complexity to a system that can be explained by known physics. The implications of this debate stretch far beyond academic journals. If the or model or something like it is correct, it would revolutionize our understanding of free will. In a purely classical, deterministic brain, every thought and decision could be seen as the inevitable result of prior causes, a chain of billiard ball collisions between neurons. But if quantum indeterminacy is woven into the fabric of our neural processes, it could provide a mechanism for genuine, non-deterministic choice, where the mind is not just a calculator but a true originator of action. It would also have profound consequences for artificial intelligence. It suggests that creating a truly conscious machine might require more than just building the right software algorithm on a classical computer. It might require building a quantum computer that can harness these same non-algorithmic processes. Our very concept of identity would be transformed, suggesting that the self is not just a pattern of information, but is intimately connected to the most fundamental and least understood level of physical reality. Whether or ultimately proves to be correct or not, it stands as a bold testament to our relentless drive to solve the deepest mystery of all, the mystery of our own inner light. But if black holes represent the universe's ultimate one-way street, a cosmic drain from which nothing returns, then what would it look like if we could hit rewind on that process? Imagine a celestial geyser, a fountain of space-time where matter and energy violently erupt outward into the universe, but where nothing, not even light, can ever fall in. This is not a fanciful invention. It is a serious, mathematically valid prediction of Einstein's theory of general relativity known as a white hole. In the precise equations that describe the curvature of space-time, the solutions are symmetric with respect to time. If you take the math for a black hole and literally reverse the direction of time, you get a white hole. Where a black hole's event horizon is a point of no exit, a white hole's horizon is a point of no entrance. It would be a region of space that utterly refuses any interaction, violently expelling everything that comes near it in a dazzling, energetic outburst. The theoretical possibility of white holes arises directly from the work of Carl Schwarzschild, who found the first exact solution to Einstein's field equations in 1916, describing the geometry around a spherical, non-rotating mass. This solution contained the seeds of both black holes and white holes. For decades, white holes were largely considered a mathematical curiosity, a quirky but physically impossible artifact of the equations. The reason is thermodynamics. White holes seem to violate the second law, which dictates that entropy or disorder must always increase. A white hole, spontaneously spewing out ordered matter and energy into the universe, would appear to be decreasing entropy, making it as unlikely as a shattered glass spontaneously reassembling itself. Furthermore, a white hole would be incredibly unstable. Any speck of dust or photon of light attempting to cross its horizon would carry energy, and according to general relativity, that tiny influx of energy would be enough to destabilize the white hole, causing it to collapse instantly into a black hole. This incredible fragility is the primary reason most physicists believe they cannot form or exist in our universe through any known natural process. Yet, the idea is so compelling that theorists continue to explore it, often through the lens of quantum mechanics. One of the most fascinating modern speculations comes from physicist Carlo Rovelli and his work in loop quantum gravity. This approach attempts to quantize space-time itself, suggesting it is made of tiny, discrete loops. Rovelli and his colleagues have calculated that when the intense gravitational collapse of a black hole reaches the point where general relativity predicts a singularity, a point of infinite density, quantum gravity effects might actually cause a rebound. Instead of collapsing into nothingness, the black hole would undergo a quantum bounce, transforming into a white hole and erupting back out into a different region of space-time or even a different universe. In this scenario, what we perceive as a supermassive black hole at the center of a galaxy could, over unimaginable timescales, actually be a dormant white hole, or perhaps a black hole on the verge of its cosmic rebound. This provides a potential mechanism for their existence that gets around the classical instability problem, placing their formation in the realm of quantum events that operate under different rules. This idea of a connection between black and white holes naturally leads to one of the most beloved concepts in science fiction, the wormhole or Einstein-Rosen bridge. The original mathematical solution that described a black hole also described a connection to a white hole through a theoretical throat in space-time. This would be a tunnel, a shortcut connecting two distant points in the universe or even two different universes entirely. The black hole would be the entrance, the white hole the exit. Unfortunately, this particular wormhole is not a stable gateway for adventure. It would be unstable, pinching off faster than any particle or spaceship could travel through it. However, the concept opens the door to the possibility that with the right kind of exotic matter or energy, something with negative mass or pressure, such a tunnel could be held open, creating a traversable wormhole. In this speculative framework, white holes are not just isolated cosmic fountains. They are an integral part of the plumbing of the multiverse, the visible endpoints of hidden tunnels woven through the fabric of reality. The most profound implication of white holes is the challenge they pose to our understanding of causality and the arrow of time. Physics at its most fundamental level, with the possible exception of the weak nuclear force, is time-symmetric. The equations work just as well running forward as they do backward. This suggests that the one-way flow of time we experience might not be a fundamental property of the laws themselves, but an emergent property arising from the specific initial conditions of our universe, namely, its incredibly low entropy state at the Big Bang. White holes are a stark reminder of this symmetry. They are a mirror image of black holes, and their apparent impossibility in our universe tells us less about the laws of physics and more about the specific history and structure of the cosmos we inhabit. They force us to ask if the relentless forward march of time is an absolute truth or simply a local bylaw of our particular cosmic neighborhood. This leads to a truly grand speculation. Could the Big Bang itself have been a white hole? Think about it. The Big Bang is described as a singular event from which all matter, energy, space, and time erupted into existence. This sounds remarkably similar to the description of a white hole, a point of origin from which the universe flows forth. In this model, our entire cosmos isn't expanding into nothingness. It is being emitted from a white hole singularity, the other end of a tunnel connected to a black hole in a parent universe. This idea forms the basis of the black hole cosmology, a theory suggesting that every black hole in our universe could spawn a new baby universe inside it, with its own Big Bang, its own physical constants, and its own white hole origin. We could be living inside one such universe, our entire history the result of a stellar collapse in a vastly larger meta-universe. While this remains highly speculative and far from proven, it illustrates the incredible power of white holes as a conceptual tool. They are more than just a mathematical curiosity. They are a key that unlocks new ways of thinking about the origin, structure, and ultimate fate of everything that exists, pushing our imagination to the very limits of space and time. Now, let's dive into a philosophical argument that forces us to seriously consider a possibility we often relegate to science fiction. This is the simulation argument, formalized by the philosopher Nick Bostrom at the University of Oxford, and it doesn't claim we are living in a simulation. Instead, it presents a devastatingly logical trilemma, a set of three possibilities, at least one of which must be true. Bostrom's reasoning suggests that one of the following propositions is almost certainly correct. First, that virtually every civilization at our level of technological development goes extinct before it becomes capable of creating realistic simulations of reality. Second, that even if they achieve this capability, they almost universally choose not to run such simulations. Or third, we are almost certainly living in a computer simulation right now. This isn't a wild guess. It's a structured, logical argument that forces us to confront the future of intelligence in the cosmos and our own place within it. To understand why Bostrom believes one of these three must be true, we need to follow his statistical reasoning. Let's start with the assumption that it is possible, in principle, for a sufficiently advanced civilization to create vast, detailed simulations of conscious beings. This isn't a huge leap. We are already creating increasingly sophisticated virtual realities. Now, if a civilization doesn't go extinct and does decide to run these simulations, they could potentially run a staggering number of them. A single post-human civilization might have the computing power to simulate entire planets, civilizations, or even worlds, each populated with conscious digital minds that believe their reality is real. The number of these simulated minds could quickly become astronomically larger than the number of original, biological minds that created them. Therefore, if you believe that many civilizations will reach this stage and that many will choose to run these simulations, then the number of simulated beings in the universe would vastly outnumber the real ones. So, if you were a conscious mind, the odds are overwhelming that you would be one of the simulated ones, not one of the original biological ones. The only ways to avoid this conclusion are to reject one of the premises. Either civilizations never get that far, they get there but never run the simulations, or we accept that we are likely simulated. Let's break down the first horn of this trilemma, the great filter of extinction. This proposition suggests that there is some kind of existential wall that every advancing civilization hits, a challenge so difficult that it prevents almost all of them from reaching technological maturity. This could be self-destruction through nuclear war, a climate apocalypse, or a runaway nanotechnology disaster. It could be an external threat like an asteroid impact or a gamma-ray burst. Or it could be the unforeseen consequences of their own technology. most notably the development of a superintelligent artificial intelligence that is not aligned with human values and decides to eliminate its creators. This possibility is a sobering forecast for humanity's own future. Our rapid technological progress in the 20th and 21st centuries has not been matched by a similar growth in wisdom, ethics, or global cooperation. We are playing with powerful forces that we barely understand, and this first proposition suggests that this phase of technological adolescence may be the great filter that silences the universe, explaining why we don't see any other advanced civilizations. They all destroyed themselves before they could make their presence known. The second possibility is perhaps more optimistic but equally fascinating. It suggests that civilizations do survive and attain godlike technological capabilities, but they almost unanimously choose not to create these ancestor simulations. Why might they abstain? The reasons could be ethical. A morally advanced civilization might see the creation of conscious beings in a simulated world as a form of slavery or a profound ethical violation. These simulated minds might suffer, experience pain, loss, and fear, all for the amusement or research of their creators. Would it be ethical to create a universe full of suffering, even if it is digital? Alternatively, a highly advanced civilization might find such simulations boring or pointless. They might have moved on to pursuits and experiences that are utterly incomprehensible to us, leaving behind the desire to simulate their primitive past. Or they might be concerned about a simulation within a simulation, a potential infinite regress that could destabilize their own sense of reality. This branch of the trilemma implies that the cosmos is filled with mature, wise civilizations that have consciously chosen not to play God, leaving the universe largely silent. Then we arrive at the third and most mind-bending possibility, that we are already living in a simulation. If you reject the idea that civilizations always go extinct, and you reject the idea that they always choose not to run simulations, then you are forced to accept that simulations are being run. And if simulations are being run, the number of simulated minds would be billions or trillions of times greater than base reality minds. Therefore, statistically, you are almost certainly one of those simulated beings. This isn't necessarily a depressing thought. Our creators might not be malevolent. They could be curious researchers, historians recreating their past, or even distant descendants running a cosmic version of a heritage project. The technological feasibility of this is often debated. Could you truly simulate an entire universe down to the last atom? Probably not, but you might not need to. A convincing simulation could use shortcuts, only rendering in full detail the parts that are being observed. Much like a video game only loads the part of the world the player is currently in. The rest could be run on a simpler, statistical level. The computing power required to simulate every human mind on Earth is staggering but not physically impossible according to our understanding of physics. Some estimates suggest that a planet-sized computer could do the trick. Where does this leave humanity? The simulation argument is not a proof that we are in a simulation. It is a logical framework that forces us to confront the future. It makes the simulation hypothesis a respectable subject for philosophical and even scientific inquiry. Some scientists have even proposed potential tests, looking for possible glitches in our reality or fundamental limits in resolution, like a pixelation of the universe. But its greatest power is as a mirror. It forces us to ask what we believe about our own future. Will we overcome our self-destructive tendencies? Will we develop the wisdom to wield godlike technology ethically? Or are we destined to become creators of new realities ourselves? How we answer these questions today might determine which branch of the trilemma becomes true for our civilization. It challenges us to live in a way that we would be proud of, whether we are the original creators or the created, because if we are in a simulation, our actions are being observed, and if we are not, we are the ones who will one day have to make the choice of whether to become the simulators. Imagine a pot of water you desperately want to stop from boiling. In our everyday world, staring at it intently won't change a thing. The water will heat up and eventually erupt into bubbles regardless of your watchful gaze. But shrink this scenario down to the quantum realm, and the rules of the game change entirely. Here, the simple act of observation becomes an active, powerful force that can literally freeze a system in its tracks, preventing change from happening at all. This bizarre phenomenon is known as the quantum Zeno effect, named after the ancient Greek philosopher Zeno of Elea, who proposed a series of paradoxes suggesting that motion is an illusion. If you continually observe an arrow in flight, he argued, at any single instant it is motionless, and therefore it can never actually reach its target. While Zeno was wrong about the classical world, he was, in a stunning twist of fate, accidentally right about the quantum one. The entire strange effect hinges on the most counterintuitive pillar of quantum mechanics, the collapse of the wave function. Recall that a quantum particle, like an atom or an electron, doesn't exist in a single, definite state. Instead, it exists in a blurry cloud of probabilities, a superposition of all its possible states simultaneously. This probabilistic fog is described by its wave function. It's only when we measure the particle, when we observe it, that this wave function abruptly collapses, and the particle is forced to pick a single, concrete state to be in. Now here's the key. Immediately after this measurement, the wave function starts evolving again, spreading out and exploring new possibilities. But if you measure it again and again and again in rapid succession, you keep resetting the clock. Each observation collapses the wave function back to its starting point before it has any meaningful time to evolve and change. It's like constantly asking a wandering traveler, "Where are you now?" And each time you ask, they have to stop and report their original starting location. If you ask often enough, they never actually get anywhere. The system is trapped, its evolution inhibited by the relentless gaze of the observer. The pot never boils because you keep lifting the lid to check. This isn't just an abstract theoretical idea. It was given a firm mathematical foundation by physicists George Sudarshan and Baidyanath Misra in 1977. They demonstrated that the continuous, frequent measurement of a quantum system can indeed halt its transition from one state to another. A classic example is an atom that is excited and ready to emit a photon, to decay back to its ground state. Left unobserved, it will decay in a certain predictable time, but if you bombard this atom with a continuous series of measurements, constantly asking, "Have you decayed yet?" you can effectively freeze it in its excited state, dramatically slowing down or even preventing the emission of the photon altogether. Your observation is actively keeping the atom excited. This profound effect is not confined to thought experiments. It has incredibly practical and powerful applications in the technology we use every day. Consider the atomic clocks that form the backbone of global positioning systems, the internet, and financial networks. These clocks rely on the incredibly precise vibrations of atoms like cesium or rubidium to mark the passage of time. But these atoms are susceptible to decoherence, random interactions with their environment that can slightly alter their energy states and make their vibrations less precise. By using a technique inspired by the quantum Zeno effect, scientists can effectively pin these atoms in their desired state. They don't literally look at each atom constantly, but they apply a series of carefully timed pulses of energy that mimic the effect of repeated measurements. This actively stabilizes the atoms, preventing them from drifting and ensuring the clock ticks with near-perfect accuracy. Our ability to precisely navigate with our phones and synchronize the world's digital infrastructure depends on our understanding of how to use observation to stop quantum change. The same principle is absolutely vital in the fledgling field of quantum computing. The heart of a quantum computer is the qubit, the fundamental unit of information that thrives in its fuzzy state of superposition. But this superposition is incredibly delicate. The moment a qubit interacts with its environment, be it a stray photon, a vibration, or a change in temperature, it undergoes decoherence. Its wave function collapses and it loses its quantum information, becoming a boring classical bit. This is the single biggest obstacle to building a practical quantum computer. Here, the quantum Zeno effect is flipped from a curiosity into a crucial shield. By periodically measuring the qubits in a very specific way, or by applying targeted energy pulses, engineers can actively protect them from decoherence. They use the power of observation to lock the qubits into their desired quantum states, effectively fighting off the disruptive influence of the outside world. It's a stunning paradox. We use measurement, the very thing that causes collapse, to prevent a detrimental collapse from happening, allowing the quantum computation to proceed. This is the ultimate example of the observer not just shaping reality, but actively preserving and protecting it. The implications of this stretch far beyond engineering and into the deepest questions about the nature of reality. The quantum Zeno effect blurs the line between the observer and the observed to an almost philosophical extreme. It suggests that measurement is not a passive, neutral act of discovery. It is an interactive process that fundamentally alters the system being studied. In the quantum world, you cannot be a detached spectator. You are always a participant. This forces us to reconsider the very nature of change itself. Is change an inevitable, continuous flow, or is it a stuttering, stop-motion process that only happens in the brief moments when we look away? The effect demonstrates that at its most fundamental level, the universe possesses a kind of dynamic instability, a constant tension between the potential for change and the act of witnessing that potential. It reveals a cosmos where attention itself is a force, a tool that can be wielded to either freeze a moment in time or, if used differently, to accelerate transformation, showcasing the incredible, active role consciousness and measurement play in the ongoing creation of the reality we perceive. Now let's turn our attention to a concept that sounds like it's been lifted straight from the pages of a golden age science fiction novel. A mysterious force that seems to defy gravity itself, generated by nothing more than a simple, asymmetrical capacitor. This is the Biefeld-Brown effect, and its story begins not in a modern lab, but in the 1920s with a young, visionary physicist named Thomas Townsend Brown. While still a student, Brown was experimenting with a type of capacitor known as a Coolidge tube, used in early X-ray research. He noticed something extraordinary. When he applied a high voltage to the capacitor, it exhibited a faint but persistent thrust, a force that seemed to push it toward its positive pole. Even more astonishing, this thrust appeared even in a vacuum, suggesting it wasn't just pushing against air. Brown believed he had stumbled upon a direct link between electricity and gravity, a way to manipulate gravitational fields using electric fields. He called it the gravitator, and he spent the rest of his life trying to prove it was a new form of propulsion, one that could revolutionize space travel. The basic apparatus to demonstrate this effect is deceptively simple, and you can even build a rudimentary version yourself. It's called a lifter. Take a lightweight triangular frame made of balsa wood or wire. Attach a thin wire or foil along the front edge. This will be the positive electrode or anode. Then, attach a wider strip of aluminum foil along the rear edge. This will be the negative electrode or cathode. When you connect this device to a high-voltage power source, often in the range of 20 to 50,000 volts, something magical happens. The lifter lifts. It silently rises into the air, levitating without any moving parts, flames, or exhaust. It seems to be the very picture of anti-gravity, a device that contradicts everything we know about Newton's third law. For every action, there must be an equal and opposite reaction. If it's not pushing against anything, what is it pushing against? This is the central mystery that has fueled decades of debate, controversy, and fascination. The mainstream and most widely accepted explanation for this phenomenon is firmly rooted in classical physics, specifically in a process called electrohydrodynamics, or AID. This theory states that the thrust is not anti-gravity at all, but is instead the result of a physical push against the surrounding air. Here's how it works. The intense electric field at the sharp, positive anode causes the air around it to become ionized. It strips electrons from the air molecules, creating a cloud of positively charged ions. These ions are then violently repelled away from the positive anode and strongly attracted toward the negative cathode. On their frantic journey, they collide with millions of neutral air molecules, transferring momentum to them and effectively creating a wind of charged particles jetting from the positive to the negative electrode. This ionic wind provides the thrust, much like a jet engine expels gases backward to propel itself forward. This explanation is considered solid and uncontroversial for lifters operating in the atmosphere. In fact, the effect is so well understood that it's being researched for practical applications right here on Earth, such as in ultra-quiet, solid-state cooling systems for electronics, or as a novel method for aircraft propulsion without moving parts. But here's where the plot thickens, and where Thomas Townsend Brown's original claims re-enter the conversation. Brown and a number of later researchers insisted that the effect did not disappear in a vacuum. They conducted experiments where they placed their asymmetric capacitors inside vacuum chambers, pumped out the air, and claimed that a thrust, however small, still remained. If true, this changes everything. In a hard vacuum, there is no air to ionize, no medium to create an ionic wind against. A persistent thrust in a vacuum would point to something far more profound and inexplicable. This is the heart of the controversy. Proponents of a more exotic explanation suggest that the effect might be due to a true electrogravitic coupling, a direct interaction between high-voltage electric fields and the gravitational field itself, a concept that, if verified, would shatter our current understanding of physics and open the door to genuine anti-gravity propulsion and warp drives. They point to Einstein's theory of general relativity, which describes gravity as the curvature of space-time by mass and energy. Could a sufficiently powerful and asymmetrical electric field somehow warp the local space-time fabric in a similar way, creating a thrust without propellant? This remains a highly speculative and fiercely debated idea, far outside the mainstream. The scientific community remains deeply skeptical of these exotic claims. Critics argue that the thrust measured in vacuum experiments can be attributed to experimental error, such as the effect of the high-voltage power supply leads transferring momentum, or the heating of residual gas molecules in what is never a perfect vacuum, creating a tiny thermal current. Reproducing a clean, unambiguous experiment in a high vacuum that eliminates all these confounding factors is incredibly difficult and expensive. Despite these challenges, the dream of a breakthrough propulsion technology is so powerful that research continues, often on the fringes of established science. Organizations like NASA have periodically investigated the effect under programs dedicated to exploring visionary physics, and a small but dedicated community of experimenters and theorists continue to test new configurations and models, hoping to find that one piece of undeniable evidence. The enduring allure of the Biefeld-Brown effect lies in what it represents: the tantalizing possibility of a shortcut, a key to unlocking the cosmos that doesn't require us to carry enormous tanks of fuel. The tyranny of the rocket equation, which demands that we must carry exponentially more propellant to go faster and farther, has been the single greatest constraint on human space exploration. A propulsion system that could generate thrust without expelling reaction mass would be nothing short of revolutionary, enabling journeys to the stars that are currently the stuff of dreams. Whether the Biefeld-Brown effect is ultimately explained by the elegant and well-understood principles of ion wind, or by a radical new physics that redefines gravity itself, its story is a testament to human curiosity and our relentless drive to reach beyond the known, to test the boundaries of the possible, and to never stop searching for that one incredible breakthrough that could change everything. And so we find ourselves at the end of this extraordinary journey, having ventured through 30 of the most astonishing ideas that human curiosity has ever conceived. From the spooky connection of entangled particles to the silent, invisible dominance of dark matter and energy, from the possibility that our entire reality is a simulation to the humbling thought that our consciousness might be a fleeting fluctuation in a vast cosmic void, each concept has stretched the canvas of our understanding, painting a picture of a universe that is infinitely stranger, more wondrous and more deeply interconnected than our everyday experience would ever suggest. These aren't just abstract theories confined to textbooks. They are profound invitations to see the world differently, to question the very nature of existence, time, and our own minds. They challenge the comfortable assumptions we live by, revealing a cosmos where the fundamental rules are fluid, where observation creates reality, and where the vast majority of what exists remains hidden from our view, yet dictates the fate of everything we can see. This journey underscores a powerful and beautiful truth about science itself. It is not a dusty collection of facts, but a living, breathing process of inquiry. It is a conversation that spans generations, where each new discovery peels back a layer of the cosmic onion, only to reveal deeper, more complex questions beneath. The real magic lies not in finding final answers, but in the pursuit itself, in that thrilling moment of not knowing, of standing at the edge of the unknown and feeling the pull of mystery. Every one of these mind-warping concepts began as a seemingly impossible question, a paradox that refused to fit into the established order. It is a testament to the human spirit that we lean into these mysteries rather than away from them, driven by an insatiable need to understand our place in this grand, bewildering tapestry. The greatest takeaway is that the universe is not a puzzle to be solved, but an endless story to be explored, and we are all part of its ongoing narration. Now we turn this conversation over to you. This exploration is meant to be a starting point, not a conclusion. We want to hear which of these ideas resonated with you the most. Did the infinite branching pathways of the multiverse capture your imagination? Or did the immediate personal power of the placebo effect make you reconsider the connection between your mind and body? Perhaps the chilling silence of the Fermi paradox left you pondering humanity's future, or the elegant weirdness of quantum tunneling made you appreciate the hidden magic powering the stars. Share your thoughts and reflections in the comments below. Let's continue this discussion and learn from each other's perspectives. If this journey through the cosmos's greatest mysteries sparked your curiosity, make sure to subscribe and hit the notification bell so you don't miss our next deep dive into the wonders of reality. Thank you for joining us on this intellectual adventure. Keep questioning, keep exploring, and never lose your sense of wonder at the incredible, mysterious universe we are